All right. Hello and welcome everyone to this third episode of You Wouldn't Type Check a Car. We left off last week on Sunday around some of the optimizations we were doing, and the plan today is to continue with that. Hopefully, see some better performance numbers and understand what it takes to optimize sparse computations on GPUs. I just a sort of quick update of what's been happening. I was in Chicago this whole week actually. I was attending the symposium we had for a funding agency that we have to present every year, and I was there. A really beautiful city. UIUC is in Havana-Champaign. It was really pretty. I wish I could have stayed there longer. But yeah, I just got back last night. But I did get good sleep this time, which means hopefully we won't have mistakes in our code like we did last time. Last week, I had just returned that day from Maine, and I started streaming in like a few hours after that, and that was probably a bad idea. But I have had good sleep now, so we can fix all the issues we had before, or at least talk about why those issues were happening, and then we can get into optimizing more stuff. Uh, Yes, we were talking about NVIDIA's libraries in the chat. I'm a big fan of NVIDIA in that sense. They obviously make good hardware, and they innovate a lot on the hardware. Like if you look at how much changes NVIDIA GPUs have gone in the last couple of generations, it's huge. I'm not saying like other GPU manufacturers or even like AMD is not innovating enough. It's just Nvidia has always been up there. But the sort of the other thing that has really going good for them is that they also focus a lot on the software. I mean, they have good compiler tool chains. They invest a lot of resources into creating libraries so people can use these GPUs, which also actually offers them a lot of flexibility in the hardware. In that, if you have a hardware and if you decide to add more features to it, or if you decide to remove features from it for better features, usually people complain about like backward compatibility. But because they maintain these good set of libraries, as long as you're using their libraries, even if they change the hardware, you don't actually lose any sort of compatibility. They make sure that those libraries still work with the newer hardware. And I think that's a good approach. I mean, this is not just for libraries, right? They also did it for the ISA. Last week, we looked at a little bit of PTX and SAS. I mentioned it as the same thing, but they're obviously different things. That's another strategy which NVIDIA follows so that people don't have to be too much sort of reliant on what the fixed ISA the hardware supports. So if you don't know about this, usually when you write CUDA code and it compiles down, it produces an intermediate called PTX, which is sort of portable in NVIDIA's terminology. So it sort of works on any of the GPUs. And when you actually run that, there's a driver in your Linux kernel or whatever operating system you're using that translates that PTX into SAS, and SAS is like the a hardware specific assembly that actually runs on the GPUs. But the good thing about this is they can now change the SAS specification. They can change the kernel driver without the user having to rewrite their applications, which is a really good thing. I think that's portability and focus on software tooling alongside the hardware actually puts NVIDIA into a really good position. Yes, they're at least trying to survive while AMD is totally banking on community-driven OSS. I mean, yeah, AMD is catching up at least for some markets, like some part of the markets, games and high performance computing, where it's like, I mean, previously, if you look at any of the machine learning tool chains like TensorFlow, PyTorch, they would not run on AMD GPUs. But I think recently, like you said, open source community has been making it possible for AMD to actually run these libraries. So that's a good thing. I mean, having competition is always good. But I just feel like NVIDIA's strategy on how to like make it easier for users to sort of be like continue using their hardware, I think it's really good. And yeah, I appreciate that. I mean, but they have changed things in the past too. For example, the NVVP, the tool we were using last week for the visual profiler, they have deprecated that now. They use VTune, I think that's the new one. Sorry, not VTune. VTune is the Intel one. Sorry. What is this called? There's a NVIDIA's tool which I forget now, but I've never used that. So now that if I have to use a new generation of GPUs, I would actually have to learn a new tool. If someone remembers the name of the tool, please let me know in the chat. It's been a while, but yeah, I still continue to use NVVP. But I think for the purpose of this stream, whatever optimizations we do for the V100 GPU that I have, they should actually make sense, at least if not like literally translate line by line to the new hardware. They should still make sense for the newer generation GPUs. I know that the newer generation GPUs don't have as much penalty from diversions because the hardware handles it better, but it's still a penalty. You still have to optimize for load balance, you still have to optimize for memory accesses, irregular memory accesses, and so on. So whatever we are discussing today, hopefully still remains relevant for the newer generation of GPUs to come. Okay, I'm gonna start sharing my screen, and we will get into where we left off last week. Okay, and I forgot to change my screen resolution again. Give me a second. I have an ultra wide monitor, and the stream resolution doesn't like that, so I have to change it to not be ultra wide. Oh, this one, yeah. So now it fits completely. All right. Let's get into the optimizations where we left off. I'm just gonna go back to my server. Oh, perfect. So we are right in the same file where we had left off last week. This is actually this is thanks to Screen, and this is thanks to some of the tools I have written around Stream, around Screen. What used to happen was when I started in my first year, I used to like I said in my first stream, I didn't write code on my Mac because I hated writing code on my Mac. So I used to just SSH into the servers and write and do basically all my work on the server. If I'm like moving around the campus, if I'm like going from offices to offices, the network switches sometimes because we have like multiple routers around, and that used to cause my network connection to drop. And then if I'm in the middle of editing a file, it used to crap out. The obvious solution is I have to use Screen, but I couldn't remind myself to always use a Screen session when I'm sort of like working. So what I did actually at that time was, let me show you that. Actually, let me just do this here. Uh, I built this tool called Always Connected. Actually, it should be here. Yeah, sorry. Uh, Come on. Yeah, so I built this tool called Always Connected, which basically has a bunch of like bash scripts that whenever I sort of log in, this gets inserted into your bash RC. It has an install script and everything. And whenever I sort of like connect, it automatically it maintains a pool of screens that I can sort of pick one from manually, or I can like it connects me to one of the sort of free screens that were left from last time. So for example, if I do pool now, it shows me that 0 out of 1 screens are free, which because I'm connected to the only screen that's open. But if I suppose SSH into the same server, what it's gonna do is it's first of all going to send me to a new screen session, and then it shows me that 0 out of 2 screens are free now because I'm connected to both of them. And suppose I disconnect from this one, now you can see it shows 1 out of 2 screens are free. And if I SSH again, it continues from where I had left off. So this has actually saved me so much effort and work. I wrote this, like hacked it together. I know there are good solutions. Yes, Mosh Mobile Cell actually is pretty good too. I've seen people use it. The only issue is we have a lot of servers in the lab, and I would have to go and manually install Mosh on all of them. My strategy was something that like would work automatically. So the good thing is, the other thing I didn't mention before is all of our servers have a shared home directory. So any sort of like changes I make to my bash RC actually propagates everywhere. Like all of the things see the same thing, and all Linux I mean, all of our servers come with Screen install. All of them come with SSH connections. So my solution was to insert something into my bash RC that would just like work everywhere, and that has saved me so much time. But yeah, I just like plugging in. I'll drop the actually. You know what? Let's put the links for the stuff which people have been sharing in the chat. I don't want to miss it. Matt X was okay. Let's say resources shared in the chat. Oh, sorry. Matt X was one. a simple Python script with RPC did that thing in my case. Yeah, I mean, people have written their own solutions. I am a fan of writing stuff in Bash, so I did that. Okay. Oh, sorry. By the way, this resource repository, I should also share this link for. I was looking at this before. If you go to my stream, there is this resource document. We share everything that we sort of work on is shared here. Yeah, and I'll commit today's changes once we are done. Okay, so let's go back to what we were working on. Oh, yeah, so we were working on implementing SPMV last week. I actually made some changes after we hopped off, so I should undo those changes and then we can talk about it. Okay, so where we left last week was we were first of all struggling with getting CUDA to run my kernels, and I sort of hand waved it and said, hey, it's some issue with the driver and I'll fix it later. I don't know what the issue is. And actually, it wasn't an issue with the driver, it was issue with what I was doing. The little bit of like how this whole issue came up is I have this run and time function, which basically takes an argument, a lambda, and runs it a specific number of times and times it and returns the amount of time in milliseconds it took to execute that kernel. I had written this before the stream in preparation. It's part of this utils header that I have. And I had left, so previously, if you look at the GitHub version of this, let's go to the GitHub version. Yeah, if you go to the GitHub version, you'll see that I had left a comment. Oh, actually, I updated it. Oh, well, so maybe let's look at the history for this one. Yeah, so if you look at this before, I had a comment saying it's the function's job to synchronize for CUDA. But I forgot about this. When we were writing the code, I thought that I had put CUDA device synchronize inside the run and time function. And that's why I did not CUDA synchronize. Before I sort of, I mean, in case people haven't heard about this before, CUDA device synchronize is a CUDA library function. Normally, when we launch kernels like these calls with like triple angle brackets, that is basically queues up a job onto the GPU to run. It doesn't actually this when this function call returns, it doesn't actually finish that. It doesn't wait for that function to finish, and there's a specific reason for this. This is so that you can like queue up smaller kernels before so that you don't have to wait for them to finish, and that comes in very handy. What CUDA also has this notion of streams, where you can create these separate streams and enqueue functions on different streams, and that lets you also actually have more fine-grained control on which kernel runs after the other. You can basically express dependencies better. Putting things on different stream doesn't mean that they will execute at the same time. It just means that they're not dependent, which means that they can be executed in parallel if needed, or they can be executed in any order. Like one stream is completely independent from the other. But getting back to this, normally functions don't the code doesn't wait for the function to finish, the kernel to finish. What we previously had was just this call to run on time, and I was printing the time out and I was exiting. There's two issues with that. One is the time would be wrong because we're supposed to wait for the function to finish before we actually return, right? And the second issue is what was happening before was because we were not waiting for the function to finish, depending on how the kernel scheduler worked, sometimes the process used to exit before we actually finished the kernel. And when that happens, the kernel, the CUDA driver just stops all the runs for those processes. So when we were running nvprof, we couldn't see our kernel running, and that was the issue. But then when we added so we wanted to fix, we wanted to check what was happening. So while debugging, we added a CUDA memcopy call to copy back the data from the device C buffer to the host C buffer to check if it was running correctly. In doing that, we inadvertently added a CUDA memcopy because CUDA memcopy is a synchronizing call. CUDA memcopy is one of those functions for which the program waits before it is finished. And that's actually useful, right? Because when you're doing CUDA memcopy, you're probably going to read what that value is. So CUDA memcopy implicitly synchronizes before it moves on. And that's the reason why we started getting the correct result. And I couldn't figure out what was going wrong. But anyway, I have changed that since then. I have added a CUDA device synchronize call before and after the kernel. That way we do not like have improper measurements, and also our kernel actually runs the number of time it's supposed to run. Remember, the CUDA device synchronize call needs to be added before the get time function, the start time, because any kernels that you have from before should be finished before we start timing. And then the second one should be added right before you're about to end the time. If you add it before the if you end the timer before that, you will get a wrong timer, because it will only time the amount of time it takes to sort of like just enqueue these kernels. You actually want for the kernels to finish, and then you can time them. So yeah, this code has been fixed now. We should be able to get the correct times. Okay, so nothing has changed from the last time. I've only added the CUDA synchronize call to the run and time function itself. So that way we don't have to like add it again and again in the run and time function. Anyway, so this CUDA last check error also, by the way, has to be after the CUDA device synchronize, otherwise it won't make sense. So what I'm going to do is I'm just going to peel it out, and it will tell us if there are any errors from the last call to the kernel. Okay, now let's build our code. And run SPMV again, what we wrote last time. I'm just going to make sure that no one else is using the GPUs. Okay, no one is using it. So let's see, build SPMV. And if you remember, our SPMV takes one parameter, which is the data set. So this time when we actually run it, you'll see that there is actual like a proper number, unlike what we had seen before. Last time we were seeing like very small numbers. That was because of the enqueue time. And if I actually run this again and again, it gives me stable numbers. So you can see these numbers are pretty stable now. So we are doing the things correctly. And to remind you, there are two sort of executions here. The first one is running a basic scheduler or basic load balance strategy, where we are mapping each row of the matrix to different thread on the GPU, and all the non-zeros in that row are handled by the same thread. This has multiple issues we talked about. One is load balance, obviously, in that because different threads in the warp are doing different amount of work, mainly because different rows have different amount of non-zeros to process. This leads to a lot of load imbalance. And what happens because of load imbalance is that different threads are doing different amount of work, which means one thread has to wait before the other thread is done with its operation. And because these GPUs are massively parallel, usually one thread blocks a bunch of threads. That's a lot of compute wasted. You could have done work on that in the meantime, which is why the performance is kind of bad. And the other issue we saw in the visual profiler last time was that the memory accesses we do this way are actually very non-coalesced, because each thread is accessing a different non-zero. But neighboring threads in a warp are not actually accessing neighboring memory, which is useful for the GPU to optimize your memory accesses. And those two combined effects was making this incredibly slow. Okay, there's a comment in the chat. Can Hyperfine work here? We need to average upon different runs here. I haven't used Hyperfine. I'll check it out. Thanks for the research, but I'll make sure. This is averaged, by the way. This is averaged over like number of runs that the user specifies, in this case I'm specifying the number of runs to be 100. So it is still averaged over 100 runs, and 100 runs is typically good enough for these kind of kernels. This graph is kind of big. If you look at the number of vertices, it has okay, by the way, I'm using matrices and graphs interchangeably here. So apologies about that, mainly because I came from, like, I learned all these things in the context of graph algorithms, so it's natural for me to think about it as graphs with edges and so on. But the same logic sort of translates to, or the same ideas translate to sparse tensors with rows and columns. So when I say rows, it typically means like the vertices of a graph, and the columns are sort of the destinations of the edges, the neighboring vertices of that row. So I'll try to not mix terminology too much. I'll try to stick with the matrix terminology, but in case I accidentally say like graph somewhere, please read it as like matrix, a two rank matrix, or a two rank tensor. So yeah, this data set that we're using is called the SOC Live Journal data set, which is actually a graph data set. It's a graph of some social network. I don't remember exactly what it is, but yeah, it has 4.8 million rows in the matrix and about 85 million edges or non-zeros in the whole matrix. That is a lot of kernel. So running it 100 times actually gives us pretty stable results. So yeah, if I run this again, it gives me about the same time. Yeah, so now that we have an understanding of what went wrong the last time and we have fixed it a little bit, let's go back to the code. We actually ended the stream too early. I mean, I wanted to cover this one thing before we moved on, which is if you look at, if there are any questions about this, by the way, please drop it in the chat. I'll answer them as we go. But let's look at the two versions that we wrote the last time. I'm gonna remove this just to not spoil things for everyone. So we had basically the first version where each thread handles an entire row and updates the output for that row. So you can see RID equals to thread ID, and then we are doing writes on D underscore C of RID. What this means is exactly one thread is writing to a particular memory location DC D underscore C. This is great because now you don't need to sort of, you don't have to worry about two threads writing to the same memory location at the same time. But then we changed the implementation. We added this warp thing where multiple threads in a warp are working on the same RID and the row ID. And the way we know that is by looking at this. We are doing RID equals to thread ID divided by 32. And this is integer division, which means that any value from say 32 to 63 is going to have RID equals 1. So multiple threads, in fact 32 threads, are all working on the same output. And the way we know that is here is the write on those values. We have DC underscore RID plus equals. Now multiple threads from the same warp are actually writing to the same location in memory. This is bad. This is bad for, I mean, this is bad because now you could have errors. You could have read, so you know what read after writes kind of stuff. So, okay, what is a plus equals, right? It's a read, it's a add, and it's a write. If you have if you don't use atomic accesses and if you just do it in parallel, it could happen that two threads could read at the same time and then add and then they write back their own values, which means you will miss some updates. This is classic concurrency stuff that we need to deal with, and we did not deal with last time. My plan was to like once we run it, go back and fix this, but we never got to it. We actually had a same issue here too, where I did not have this if lane ID check. It was just like this. This is actually not too bad. This is what is called a benign race, where we're just writing zero in that same location from multiple threads. It's bad for like performance reason. It depends on if they're like different threads, different thread from different warps or different CTAs and stuff like that. In this case, it's not too bad for performance, but the idea is we shouldn't be doing this. We shouldn't be writing from the multiple threads. So I added this check, which is if lane ID, where lane ID is like the ID of the thread within that warp. So lane ID is thread ID modulo 32. If lane ID is 0, only then you write to it. So other warps are not writing to the same memory location as the first thread, as the first lane. And now this needs to be changed. Can we add like a similar check here? Can we like just add a check saying if lane ID equals to 0, then write? No, obviously, because then we would miss some of the updates, and we don't want that to happen. So what CUDA has this useful function called atomic add, which actually let's pull up the description for atomic add. It's actually like an intrinsic which I do not have it here. Okay, actually, atomic add is one of the library functions. The question, the idea of pointer chasing on data structures like is there any impact on it? I'll get to that. I'll get to that. We'll get to pointer chasing and stuff like that later, but thanks for the question. I'll address that. So yeah, atomic add is a function that NVIDIA library provides. It takes in the come on, the address of the memory location that you want to write to and a value you want to add, and it returns the old value. So it returns what the old value was before this add was done. So what we will do is we will use this function to accumulate those values in this memory location instead of like doing a normal add. Okay, this ideally I mean, previously our result was still fine, and that just happened to be correct just because of the way this GPU hardware works, but it's not guaranteed to. If you're doing multiple accesses, you should be using atomic accesses. It's a quirk of some of the hardwares in the way that access still turns out to be right, but we shouldn't rely on that. There are reasons where it could fail. So now that if we compile the same thing again, by the way, the hardware didn't warn us or anything about it. There are tools to find these kind of raised bugs. I'm not using them right now. But now if we run the same kernel, we'll see that it actually runs a bit slower. It actually runs around 50% slower than before, like 150 times 150% slower than before. And why does that happen? It's because atomic accesses are inherently expensive. But we had to add this atomic access because multiple threads are now working on the same memory location. You should be using atomic access for correctness. Previously, we got some improvements, but that was a wrong code because it could go wrong in certain scenarios. So this is our sort of like fixed version. It became slower, but it still produces correct result now. Yeah, atomic add CAS on GPU atomic sounds exciting. Yes, GPUs actually have a CAS instruction too, and you can build all sort of primitives out of CAS if you know about this. And I have done that before, so we have implemented like min reductions and so on. For example, when you write SSSP, which is single shortest path, you don't actually do atomic add, you do an atomic min because you have multiple threads trying to update the current shortest distance for a vertex in a graph, and the way they do that is by calculating the new path's distance and doing a min with the correct distance. And we don't have an atomic min function in CUDA built in, so we implemented using CAS. It's very handy, and it's fun because I mean atomics become even more necessary when you have a large number of threads like this. Okay, so the next thing I'm gonna actually, before we go ahead, there's another strategy we could have adopted to actually fix this. What we are trying to do here is we are trying to do sums across the different lanes of the warp into the same memory location. We didn't necessarily have to use atomic add here. What we could also done is done what is called a parallel reduction, which is basically each thread has a different value to store in the warp. We could have used some sort of warp shuffles to aggregate the value in the first lane and then return it to the memory location using just one of the threads, not using all of the threads. That has some performance trade-offs. I think for this particular implementation, atomic add is good enough. In fact, if you use that one, it's slightly slower because you have to write a loop for that, and it turns out atomic add is a better choice here. So, but we will see that. We will see it in one of the warp mapping load balance that we are implementing. We'll see it in that. Okay, so this one, now we solved a couple of issues. We now have there's actually two things we have solved somewhat. One is that these accesses into the column and value arrays are now contiguous. Because if you think about this, CIDX is going from like the row pointer plus lane ID, which means the lane ID, the lanes will access locations like 0, 1, 2, 3 at the same time, because we are adding sort of what location they're accessing is added with plus lane ID. That means they're doing memory access that are contiguous in memory, and that's good. That's one of the things we solved. And the second thing we actually ended up solving was now that warps, the threads in a warp are actually working on the same row, they are not sort of hurt by the different number of non-zeros in a different row. So like suppose row 1 has 50 non-zeros and row 2 has say 10,000 non-zeros. Previously, two threads in the same warp would now be stuck because one is done, the other is waiting. That doesn't happen as much anymore because now the 32 threads in a warp are all collaboratively doing the 50 non-zeros from the first one, and different warp is doing the 10,000. So that warp will run longer, but this warp will be done. Now, imbalance between warps is still bad. Like we don't want that. We want all the threads in the GPU to have the same amount of work to be done. But imbalance between warp, like within the warp, threads in the same warp actually hurts a lot more than imbalance across the warps. Imbalance across warps is also bad because we need to have enough warps in flight for the GPU to be saturated, and if we don't have that, it kills the performance. But even then, load balance, this balance between the threads in the same warp is actually worse. So we solved that to some extent. We don't have that much imbalance anymore, and that actually boosted our performance a lot. From like it's almost what 5x the performance or 4x the performance of what we had before, which is great. But what's the issue here still? Now, I talked about this case that multiple threads in the same warp, 32 threads to be specific, are handling the non-zeros in the same row. Now, what if your thread has 63 non-zeros? What happens in that case? In the first iteration of this loop, all the threads handle one non-zero, which is done here, and in the second iteration, all but the last thread handles one non-zero. The last thread won't do anything because we have a condition here saying CIDX is less than a dot like the row pointer of the next vertex, which means because there are only 63 elements to process in that row, the last thread will basically just stay silent or stay dormant. This problem gets worse if your sort of non-zeros is like say 33. In that case, all of them do one iteration, and in the second iteration, 31 threads are sitting silent while one thread is trying to do something. And for like vertices with less non-zeros or rows with less non-zeros, that's actually really bad. That still leads to a lot of load imbalance, is basically what I'm trying to get at. And we will try to fix that using the next strategy that we'll implement. Any questions about this? Please feel free to ask them in the chat. I'll try to go like slower if needed. But okay, so far we realize that there is still some more load imbalance to handle. And the way we are going to take care of that is by using a load balance strategy called warp mapping. Last week we talked about this warp mapping strategy. Let me actually pull that up. It was in the paper that I shared. Yeah, so if you look at this G-Switch paper, they talk about this warp mapping strategy. And our paper actually borrows the strategy from them and cites them. So the warp mapping method redresses the imbalance in a warp. So that's what we are trying to address. A warp processes continuous vertices from active set as a batch. It loads the warp size of their neighbors into the GPU shared memory each time until all their neighbors have been processed. A binary search on the loaded edges is performed to find the source of the neighbors. Finally, the results are returned back to memory. So at a high level, the goal is to make sure that all the threads in the warp are doing the same amount of work. And the way it does that is by sort of redistributing the non-zeros from different vertices among the threads in a warp. So for example, let me actually go to the drawing board for this one, and then it will be clearer. I mean, they have this figure here. It's not the easiest to understand because they talk about the whole application, but let me draw what we need. Okay, let me pull up. I'm using Zoom to share my iPad, by the way. If someone knows of a better tool, please let me know. I tried out some of them. They weren't as stable. They used to work weird. So I switched back to using Zoom. But if there are any better ways to share my iPad screen on my monitor, that would be really helpful. Pulling up my screen. Okay. Goes here. Okay. Yeah, I hope you folks can see my screen. I think you can. Okay, let's draw what happens when we have a different number of non-zeros to process. So what I'm going to do is I'm going to actually describe the problem this way. So suppose here is the set of rows we have to process. In this array, I'm going to write how many non-zeros are there in that row. So let's say the first one has 3, the second one has 52, the third one has 10, 11, 0 is not going to happen because we are storing it in sparse. Let's say 1, and let's say 12. So these are the number of these are the rows. So 0, 1, 2, 3, 4, 5 rows, and these are the non-zeros. These are the non-zeros in that row. And we want to process all of these non-zeros. Suppose this is the entirety of our matrix. How do we make sure that Actually, there could be a zero because we are storing it in CSR format, which means that the outer level still has the row. One of the rows could have a like a zero number of non-zeros to process. So what happens in this case? How do I make sure that all the threads in the warp are doing the same amount of work? Okay, if we think if we apply what we have done so far is we have mapped all these individual non-zeros to separate warps. So we have a set of 32 threads, all of which are processing this 3, and then a separate group of 32 threads that are processing these 52, and so on and so forth. And this we have realized is bad for performance because there's still some load imbalance in there. So what I'm going to do is I'm going to introduce the new strategy, which is to try to load balance this. So the first thing we're going to do is, like this paper mentions, we're going to do a prefix sum on those values. So what that means is we're going to create a sort of running sum of these values. I'm going to write that here. So it's like 355, sorry, 65, 76, 76, 88. What this running sum is basically the sum of all the values up to that point. Now, why is this important? This actually lets us now sort of let us know what the total amount of work is first of all. So 88 is the total number of non-zeros we have to process. If we divide that by the number of threads we have, we know how much work each thread should be doing. And now we can sort of, now each thread can sort of binary search into this array to figure out where it should start its work. So suppose we have a total of 3 threads, right? And we have 88 work units to process. We're gonna roughly round this up to say 80, what's the 87, right? 87. Let's think about that one later. Suppose we have 87 non-zeros. We divide them equally into threes, so we get what 20. What is it, 20? Is 87 multiple of 3? Yes, it is 29. So we have 29 amount of work that need to be done by each vertex. So now by each thread. So now what each thread does is it sort of binary searches into this array of prefix sums to figure out where it should start. So the first thread comes along and says, okay, I'm going to look for where 29 amount of work ends. And if you do a binary search in this, it realizes it's somewhere between here. So it's between 3 and 55. The second one comes and says, okay, my job is to do 29 times 2, which is 58. I'm going to see where that is. So it says it's here. And it's going to sort of, okay, so I have to do some of the vertices of the second vertex and some of the vertices of the third one, and the last one finds it finds it here. Now if you look at this, these actually the majority of the edges were anyway in this vertex, and our distribution now assigns equal amount of work to all of them. Like the first one says I'm going to do the 3 of the first one, and then I'm going to do the remaining 26 from the second one. So 3 26, the first one does that. The second one says I'm going to do the remaining how many 29, sorry, not 29, yeah, 29 from the second one, and the third one just does the remaining all of the remaining 29. So goes here, unless I missed something. Oh no, sorry. So the second one only has 52. 52 minus 26 is 26. So it says I'm going to do the remaining 26 and 3 from the next one. And then the third one says I'm going to do the remaining 7 from the next one, 11, 0, and 12. And if you add these up, it comes to 29, 29, and this is 12 plus 11 plus 7, 29. And then the last one we can sort of approximate it and give it to one of them. So by sort of like creating a prefix sum of the amount of work that needs to be done. Oh, you're not able to see my face? Interesting. I was looking down, so maybe that's the reason. But anyway, so yeah, that gives us a total of like how we distribute the non-zeros between the threads so that all of them have to do equal amount of work. This let me hide the thing again. Yeah, if you look at this paper, it talks about the same thing. It basically has a set of active vertices that needs to be processed. They're sort of non-zeros that need to be done. It creates the prefix sum again. I mean, that's what the strategy describes anyway, right? It says it loads the warp size of neighbors into memory each time until all their neighbors have been processed. A binary search on the loaded edges is performed to find the source of those neighbors. So the binary search tells you which vertex you need to start from, and finally the results are returned back to global memory. So let's implement this. Let's see what it takes to implement this warp mapping strategy. This is called warp mapping, by the way. It's implemented in Graphit too as one of the load balancing strategies that we support. Let's see if it improves our performance. I'm not guaranteeing it would improve performance. There are different data sets that sort of like behave differently, and that's part of the reason we wrote the Graphit compiler. So you can sort of like mix and match strategies and see what performs the best for your application. But let's still go back and implement this strategy and see how well or worse it performs. So this is a little bit of a complicated strategy, so like sort of bear with me. This is going to be a little bit like of a heavy implementation, but I have a sort of I have a hold on. I'm going to stop sharing. Yeah, I have a reference implementation written down, so if things go wrong, I can always look at it and we can work on it together. But yeah, so let's this new implementation is also going to have the same interface, so it's going to be spmv underscore wm. It's going to take the matrix that we are processing. It's going to take the same you know what, let's just copy this. Didn't need this num blocks, by the way. I added it last time while we were debugging, so I'm going to remove that. And this is going to be called spmvwm. Okay, so we talked about this prefix sum that we have to create, right? This prefix sum needs to be stored somewhere. Now we could allocate a piece of memory and give it off to the GPU to fill it up with prefix sums and so on. But that's expensive. Global memory accesses, like we talked about before, are very expensive. So we want to be able to like this is a very like a temporary operation, right? We don't need to save this for later or anything like that. We just want to do a prefix sum, quickly binary search into it, and be done with it. So why do we want to go to the global memory for that? What the GPU supports is something called a shared memory, which is basically like a scratch pad. NVIDIA GPUs use this terminology. I'm sure the other GPUs have something similar, but they call it something else. Shared memory is basically a scratchpad memory that's very close to the chip. In fact, it's the same hardware as your L1 cache. But the good thing about it is programmable, which means you can it's like explicitly managed. So you can decide what goes into that memory as opposed to like caches just being implicitly filled by whatever values you access. And this is very useful. Now you can sort of like keep temporary data structures very close to the chip, and they can be like fetched and returned to very quickly. The shared memory, by the way, also doesn't suffer from the problem of the global memory accesses that we had seen before, like the uncoalesced memory accesses. It doesn't suffer from that. You can write and read from them in any order, and there is no performance. I mean, there is a performance penalty with like there are some minor issues, but they are very small as compared to the global memory issues that we have. So shared memory is great if you don't want to like have this data lying around later, and also if it's also obviously smaller than your global memory, and the benefit is that you can access it very quickly, almost as like the L1 latency of your GPU. So what we're going to do is we're going to compute this per warp per warp prefix sum into the shared memory. But you cannot allocate shared memory at the granularity of a warp. So we're going to allocate it for the entire CTA or the entire thread block. And then we're just going to partition it and use it differently. So the way what this is going to hold is the number of non-zeros each vertex has. So I'm going to make UN32 because that's good enough. And then the way you declare it is with this underscore underscore shared attribute on the declaration, and I'm going to call it let's say degrees, because we're going to actually let's call it shared underscore degrees. So we're going to hold to start with, we're going to hold how many non-zeros that row has, and then we're going to create the prefix sum in place. And the size of this would be CTA size. So usually because our CTA size is 512, that's what we are launching. I'm going to set it this. Actually, you know what? Let's make it into a macro so it's easy to change it later. So we can also play around with this value and see if we get any better results. This call launch, I'm going to keep it the same, but later we'll change it to just using the CTA size. Okay, so we have allocated an array of 32 elements where we can store the values. Uh, what we need along with this is also to remember what the ID of that row was. We want to remember which row we are processing correspondingly. So I'm going to also make another shared memory array, which is going to store the row ID. So same size. And finally, I'm also going to store where does this row begin? So like we're going to event like this value, basically this row pointer's value. I'm also going to store it in the share memory because eventually we will need to read this to process the non-zeros from that row. So we need to know where do the non-zeros for this row begin. So I'm going to store another shared memory array. Let's call it shared RPTR, okay, of CTA size. So this is great. Now we have three arrays. They are very small, by the way. 512 bytes, three arrays, 512 elements, even 32s is not enough to fill the shared memory. So we have enough memory available to do this. Now we need to first, before we start processing, each warp needs to sort of load this up with the data. What we need to first have is similarly just have the thread ID. We always need that. I'm going to put this here. And then we also going to need the lane ID. So lane ID is equals to thread ID divided by modulo 32. So we know which lane we are working with. I would also, yeah, let's also make a new variable called chunk ID, which is basically saying which warp you essentially belong to. So that's going to be thread ID. Actually, this chunk ID, I'm going to keep it local to the thread. So to the CTA. So this is like offsets into these pointers basically where yours starts. So I'm going to call it chunk ID equals to thread ID x dot x slash 32. So this tells us within a CTA what is your warp ID in some sense. It's not the global warp ID. It's within that CTA. What's your within the thread block? What's your what's your thread ID? So a warp ID. So this is going to be useful because we'll be using this to index into these arrays. I'm also going to make another offset called chunk offset, which is basically just chunk ID into 32. So that like we can have a handy value for where to start indexing from. Remember, these variables that we are creating, don't worry about like creating too many variables and computations. If they're not used, the CUDA compiler will optimize it away. Also, allocating a few more registers, doing a few more operations is not too bad because unlike other GPU operations, this is a sparse computation. Sparse computations are typically bottlenecked by like memory accesses, right? Because we have this lot of indirect accesses. Every single computation needs to do like 2 or 3 memory accesses, which cannot be predicted either because there's like indirect accesses, and that's where the sort of bottleneck shows up. So if we do a few more like these divisions and multiplications, it doesn't hurt or even change the performance at all. And if it's not being used, the compiler will optimize it away. So that's good for us. Be brave while creating these temporaries like this. Okay, now that we have sort of created this array, we need to fill it up with the data that it needs to have for the corresponding vertices. So what we're going to do is, first of all, we don't want to access, we want all the threads to be running, but we don't want to touch memory touch data that's outside the bounds. So remember, when we launch those kernels, we'll launch threads that's upper sort of ceiling of the number of elements to be processed, which means we will have some threads that do not actually have vertices or rows corresponding to them. So we should not like index into the array outside the bounds of the number of vertices, but we still have those threads. And unlike the previous cases where we just had if RID is greater than number of zeros return, or if TID, a thread ID is greater than number of rows return, we won't do the same this time because we still want those extra threads to hang around. We're going to collaboratively process the non-zeros. So we still want to make use of those threads. So we're not going to exit the warps that are running like we're not going to exit the threads that don't have a vertex for them, but we won't use them for loading anything. So I'm just going to simply say if thread ID is less than num rows, which means we have something to load. I'm going to say shared underscore row equals shared underscore row of thread idx dot x is a chunk of warp. Yeah, chunk is it's a chunk of memory assigned to that warp. That's what I'm thinking. That's what I'm calling it here. Yeah, I mean in this one it is the warp ID within the thread. But the way I'm going to be using this chunk ID variable is to index into these pointers. So which because we cannot allocate like shared memories for specific warps, we can only allocate a shared memory for the entire thread block. So these are basically our way of partitioning that shared memory so different warps have their own chunk. So it's a chunk of the memory in that sense. Okay, so what I'm going to do is I'm going to say a shared row of thread id x equals this is the row id, so the vertex that we are loading. So this is just going to be simply thread id. Uh, because if thread ID is less than number of rows, we basically loaded that vertex ID into the shared memory. Now we're going to load the row pointer for this. This is straightforward. This also thread ID x dot x equals let's see. So we have a dot d underscore row ptrs of thread underscore ID. Uh, This is the same value that we use to iterate over the non-zeros here, by the way. We're just loading it into the shared memory so we have easy access to it later. We don't want to load this again and again. Because multiple threads would be loading this, by the way. Because multiple threads are going to be accessing the same memory, we don't want them to sort of load the same value again and again. So we move it in the shared memory. Shared memory accesses are cheaper, so this is better for us. And finally, we need the degree of this vertex, which is a degree of this row, which is how many non-zeros this has to process. This is going to be equals to a dot d underscore row ptrs of thread id plus 1 minus a dot d row ptrs of thread id. Yeah. If you remember, these row pointers tell us the index of the non-zeros that belong to this row into the values array. If you subtract those indices for the next vertex and this vertex, it will tell you how many non-zeros are there in this particular row. Okay, so now I'm going to just move this a little bit ahead so you guys can see this more clearly. Now we have loaded a bunch of like elements to process in our shared memory. Now we have to do a prefix sum, and we have to do a oh, oops, this should be degree. Yeah. So the prefix sum needs to be done on this array, on this specific array, because this is the one that holds how many non-zeros are there in that row. So what I'm going to do is there are multiple ways you can implement prefix sum. I'm going to, because this prefix sum is local to the warp, I'm going to use like a you'll see the kind of technique that I'll use. I'll write it first and then maybe we can explain it on whiteboard how it works. Okay. So let's see. So what we're gonna do is I'm gonna write a for loop for. So the question is thread ID plus one always safe to access? That's a good question. Why is thread ID plus one always safe to access? So we have checked here that thread ID is less than number of rows. And we know from the last time when okay, let's look at the include matrix. This row pointers array has one more element than number of rows. So this is how we know that thread ID plus one is always safe to access. It contains the row offsets, and the last one contains the final row offset, which is like total number of elements in some way. So yeah, this is this we don't need to. Yeah. Uh, okay. So let's implement. Let's see the prefix sum, right? Okay, so I'm going to do uint32t I, which is basically so yeah. Let bear with me for a second here. I'm going to explain how this works. This is going to be this. T is less than uh, t is less than 32. D multiplied equals to 2. So this is going to run 5 times. And then I'm going to do 20 plus equals 32 20 equals roughly sync. I'm going to explain all this well, sync sign 1. Let's see, what values are we contributing? We're contributing degree of and load this value locally. Oh, by the way, the else condition should also write something. The threads that are not within this should just write zeros. Sorry about that. For the vertex ID, we can write -1, and for the degree and for the row pointers, we can write 0. This is important. Otherwise, you'll have bad value, junk value. So yeah, just initializing. Okay, this has the degree of that vertex loaded. Then I can just do degree here, and this comes from b by 2. And then I can do degree plus equals to pmt. Okay, let's see what this does for us. Starting from 1. Okay, so let me actually share my screen again, and we will talk about how this does prefix sum. Okay, so suppose we have a bunch of elements. Suppose I have 8 elements. Okay, 1 2 3 4 5 6 7. Okay, so suppose I have elements 1 3 7 0 2 5 1 6. Yeah, 1 2 3 4 5. Yeah, okay. Suppose I want to do the prefix sum for this. What's the regular way we could do? We could write a for loop that goes from this to this and add the elements so far up and write at that value. So we could say for I equals to 0 to 8, a of I plus equals sum, and then actually no, let's do this. We could say sum plus equals a of I, and then a of I equals to sum. Right? We could do this, and then sum equals to 0. This would give us the prefix sum. I hope you guys can see my handwriting. It's terrible. But what I'm saying is I'm doing like a running sum and storing it at the corresponding elements of the array. This could work, but if you look at this, this takes order of number of like elements to sum this up. You could do this faster. You can do the prefix sum faster if you have parallelization available to you, and we have a lot of threads available, so we can do this in parallel. The way you can do this in parallel is there's like a lot of material about this, by the way. Nvidia also has a blog post about how this prefix sum can be done efficiently, and there are like multiple strategies based on if you're summing across threads in a warp, or if you're summing across threads in a CTA or across the global stuff. There's lots of optimizations, but what we can do now is we use this shuffle sync up instruction. Where is d declared? Oh shit, I did to call this d. My bad. This was d. D equals to 1, d is less than 32, d times equals to 2. So in the first iteration, d is gonna be 1. What this? Okay. Start from 1. Okay, yeah. So I'm going to change this a little bit. So okay, what this does is we for each of these two pairs, we are going to add the values up. So we're going to send this 1 to this 3 and store it here. So this 1 is going to remain as it is, and this is going to become 4. This 7 gets sent here, and this remains 7. This becomes 0. This gets sent here. 2 becomes 7, 1 gets sent here, so 1 becomes 7. So in the first round of iteration, we're going to add 2 consecutive values. And this is what this shuffle sync up does. Shuffle sync up is a primitive for allowing you to exchange values between the threads in a war. The first argument to this primitive is a mask. It just says what are the threads that are participating. So what I've done is I've just casted -1 to unsigned. That basically creates FFFFF. So that's basically saying all the threads in this warp are participating in this shuffle sync. The second is the value you're contributing. So it's your current value that you're sort of sending to the other threads. That is your sort of like value you're sending. And the other is how far like up do you want to receive it. So it's saying how far up ahead do you want to send this value. So in the first step, you want to send it up one step. So thread 0 will send it to thread 1. Thread 1 will send it to thread 2. Thread 2 will send it to thread 3, and so on and so forth. Can you show the code? Oh, obviously I have the code hidden. Yeah. So here we have d equals to 1, d going to 32, d multiplies equals to. In the first step, when d is equals to 1, this is the mask is set to FFF, which means all threads are participating. The value you are contributing is degree, which is the current value that you want to sort of do a prefix sum on. And the d is how far up do you want to send it, like how far up ahead in the warp do you want to send it. Because first step it's 1, so thread lane 1 sends it to lane 1, lane 0 sends it to lane 1, 1 to 2, 2 to 3, and so on and so forth. And then what we do there is we accumulate that value into your current sum. So that's what we did before. Like after the first transformation, you basically have values sent up one step ahead. And okay, let me bring my board back up again. Yeah, so let me actually draw this more clearly. Okay, so actually, should I make this a bit smaller? Yeah. So what we did is we sent this value here, this here, this here, this here, this here, this here, and this here. So we basically send the values one step up. So the new values now would be 1 would remain 1, this would become 4, this would become 10, this would become 7, this would become 2, this would become 7, 6, and 7, right? So the consecutive elements have been added into the next element. Now what we're going to do is we're going to send the value 2 ahead. So this is going to send the value here, this is going to send the value here, 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 here. So now if you do that, because now d is 2, right? D in this iteration becomes 2 now, and when you send the value 2 step up, we get 1 remains 1. 4 doesn't get a value from before, so 4 still remains 4. 10 becomes 11, 7 becomes 11, 2 becomes 12, 7 becomes 14, 6 becomes 8, and this 7 becomes 14. Okay, so we have added 2 steps at a time now. Now we're going to make it 4. So now it's going to send this here, here, and so on. So 1, 1, 4, 11 remain the same. This one gets 15. This 12 becomes 16. Oops, sorry. So 12 becomes 16. 14 becomes 14 plus 11 is 25. 8 becomes 8 plus 11. Is that right? Yeah, 8 plus 11 is 19. 14 plus 12 is 26. So this is the second step. And the third step, you're just going to add 8. So you're just going to send the values 8 step ahead. So that is going to become 1, 1, 4, 11, 15, 16, 25, 19, and 26 gets from 8 step below, so that's 27. And if you look at our prefix sums now, I messed something up. 1, 4, 11. Wait, how did I get a 15 here? This is a 0, right? This one was a 0. So 1, 3, 11 is correct. 1, 4, 11 is correct. I got a 15 somehow. Let me do this again. Sorry, I did some calculations errors while writing it out. I won't write this clearly again. Sorry. Can't read my own handwriting. 1, 3, 7, 0, 2, 5, 1, 6. Okay. So the first step, values are sent one step ahead. So 1, 4, 10, 7, 2, 7, 6, 6. Yeah, I made a mistake before. Okay, this is better. Okay, now we're going to send values two step ahead. So it's going to become 1, 4, 11, 11, 2 plus 10, 12, 7 plus 7, 14, 6 plus 2, 8, 6 plus 7, 13. Okay, and now we're going to do four steps ahead. So 1, 4, 11, 11, 13, 14 plus 4, 18, 8 plus 11, 19, 13 plus 11, 24. Okay, and finally we're going to just add the last value. So it's going to be 1, 4, 11, 11, 13, 18, 19, and 25. Now let's look at what we were supposed to have. We were supposed to have 1, 4, 11, 11, 13, 18, 19, 19 plus 6, 25. Yeah, that's what we got. So prefix sums are correct if you look at this. So what this essentially does is basically does a tree reduction. You like sum up these two values first, then you sum up these two values, and then you finally sum, when it's 8, I missed a mistake. So if you have 8 values, you have these summed up, these summed up, these summed up, these summed up, and these get summed, then these get summed, and finally these two get summed, and finally get like this stored in the last location. This is how basically the prefix sum works. Can you share all the algorithms at the repo? You mean like the explanation of this or the code for this? Because the code of all this would go into the resource in the current repo that we are working on. Okay, so we have basically, I showed an example with 8, but 32 it generalizes the same way. We just need 5 steps for it. But the idea is now that we did the whole prefix sum with just log n number of elements. So if we had explanation comment, sure. What I'll do is I'll write this out, and I'll also take the picture and put it in the resource repo so you guys can look at it later. Hopefully that's useful. Okay, I'm gonna stop sharing my screen and let's continue the implementation. So we have done a prefix sum of the values now, and they are all stored in the degree array, right? This is, where did I have this put up? Okay, next up what we're going to do now is once we have the prefix sum created, we just need to do some adjustments. We first of all need to you're missing an index into degree. No, degree is a local variable. Degree is just a variable that each thread has for accumulation. We are going to write this value back again, by the way. So, but we're not going to write it back immediately. We're going to do some changes. We have created the prefix sum sort of at the location. We need to send it a little bit ahead. We need to like sort of we need to send the value to the next warp. Actually, it's not stored at the location, it's stored at the next location. So that's again one of the shuffles will do that for us. But before we do that, we also need to let every thread know what the total degree is, so that they can know how much work they have to do. So I'm going to make another variable called total degree, which is going to be, we're just going to use a shuffle. So shuffle is like, we're going to use shuffle sync, so the threads also synchronize. Shuffle sync is just like shuffle up, but instead of taking like the up and down value of like how far you have to send, it takes the exact lane ID from which the value needs to be fetched. So I'm going to say degree, and I'm going to say 31. So everyone is going to pull the value from the lane 31. So lane 31 sends its degree, and everyone receives it from 31. And this way, basically now everyone has total degree. Because if you look at the prefix sum, the last value is the total degree. Now every thread has a total degree, which is good. Now we have to store these values back. But before we store them back again, like I said, it has to be shifted further a little bit. So the way I'm gonna, there's a message in the chat now. So the way I'm gonna do that is I'm gonna say the last thread ID, if lane ID equals 31, I'm going to set your degree to be 0. Because so everyone is going to send it one up ahead. The first one has to receive it from the last one, and that should be 0. So I'm going to make the last one 0, and then everyone is going to send up ahead. So the way it would work is shared degree of thread ID X equals, oh sorry, not thread IDX. Yeah, thread IDX equals shuffle sync all the threads that are gonna participate. They're gonna send their degrees, and we're gonna take it from lane ID -1 modulo 32. Does that make sense? Uh, or we could also rewrite this as this chunk ID plus lane ID +1 modulo 32. So everyone can write to their neighbor basically. This is easier to read than the minus version. And we can just do lane ID here. Okay? So every thread reads from like the lane they are in and writes it to the next location. Actually, do we need shuffle sync for this? No, because everyone is writing this directly. We don't need to. Yeah, what I have done basically here is everyone contributes a value and the same thread reads its own value. So we don't need a shuffle sync. Like everyone is literally reading their own value. So this can just be written as degree. So everyone just goes and writes the value at the next array location. And because we have done if lane ID equals to 31, degree equals to 0, so the last thread is going to write 0. Because lane ID +1 would be 32, 32, oh, I should have put that back at here. 32 modulo 32 is 0, so it will write it back at the first location and everything is perfect. So now each warp has a prefix sum of the amount of work that warp has to do collaboratively together. Now we can actually start computing. Now we can just like go back and start writing the values, or actually do the SPMV computation that we have to do. So what I'm going to do now is first we need to compute how much work each thread has to do, right? We need to know like what every thread knows what the total degree is, but they have to sort of like figure out first where they have to start. That we'll do using the binary search. Now we also have to figure out, okay, let's write the binary search for that. So int I equals to lane ID. So they can start from the lane they are in. Like for that vertex, they can start from the lane ID. And then I is less than, let's call it CID, because this is the columns they are processing. CID is less than total degree. This is all the non-zeros that we have to process. This is not belonging to the, they're not necessarily belonging to the same no, row. So actually, let's call it NNZID. This is the total number of non-zeros that warp has to process. Now what we, is there a question? How do I feel? Okay, so for each of the thread, now we have to first identify where to start. We need to say who owns this source. So what we have done is we have made this helper function called binary search upper bound. I'm not sure writing this function, but this is the simplest binary search function that you can think of. There is basically a while loop that goes from like 0 to len, and every time it does like this len equals to len, like the simplest binary search function that you can write. It's written this way, and it does like upper bound, which means that it will tell you which vertex it belongs to. If it can't find an accurate value, it will find the upper bound of that value. So if you're like, if your value, if your array has elements like 1, 3, 7, and if you're looking for 6, it's going to give you the 7th element. It's the upper bound implementation. Okay, so now what we're going to do is we're going to figure out which which row we are processing. So let's say int RID equals binary search upper. What do we call it? Upper bound. By the way, this function was written by Changwan, one of the postdocs in my group. So attributes to him. I'll add it in the code that he wrote this. I just borrowed his implementation. This function takes three parameters. One is the array, the length of the array, and the key you're looking for. So the array is going to be shared underscore degree, but not just the shared underscore degree, our chunk of that. So I'm going to add chunk offset, which is where my array starts, right? Like each warp has its piece. So chunk offset is basically chunk ID into 32. Sorry. Okay, and then the length of this array, for now, let's assume it's 32. There is a slight issue with this being 32, but we'll fix that later. And then the value we're looking for is NNZ ID. So that particular non-zero, which row does it belong to? That's what we are looking for. And this actually returns an up, like the upper bound and the next row. So we're going to do -1 from it because, like I said, it runs upper bound. We need to know which sort of row it belongs to. So we have to do -1 here. And now we know the row ID. We know we basically know which vertex we are processing. So this is the index into the local array. This is not the actual vertex ID. So we're going to get the actual row ID, which is going to be uint. Let's call this row ID X, and let's call this row ID. So we have RID equals to shared of, what do we call it? Row of RID X. And now we're going to see where does that begin. So we need the row pointer. So rptr equals to shared of rptr of rid x plus we need to add how far we have come. So nnz id, but minus the beginning of that row. So where do we get that? Hold up, let me think about it. This is the wherever that warps the previous warp's last non-zero. So shared of degree of chunk ID, chunk offset. Okay. This is basically giving us the okay. So we are starting from NNZ ID equals to, we start from lane ID. Yeah, we're starting from NNZ ID equals to lane ID. If you just add your NNZ ID to the row pointer, this will grow. This is not like localized to that particular row. We want an index into that row. Okay, let me explain this. So shared row pointer is basically where do the non-zeros start for that particular row. If we just plainly add NNZ ID to it, this NNZ ID is sort of the global for the whole warp. It's like the non-zero for the whole warp that we have to process. It's not local to that row. So we need to subtract off the previous like the number of non-zeros that are there in the previous vertex or in the previous row. That will give us how far we are in this row. So this should probably actually also have RID X here. Sorry, yeah. So we have and this should also have chunk offset because this should also probably have chunk offset. Yeah, so row ID comes from here. This tells us what row we are processing. This tells us where the vertex starts because that's what we stored here. Uh, and this tells us the number of non-zeros. Now we are actually going to check if we are going out of bounds. So because we have more threads than this, so we do if we are already in bounds, so we can just simply do our computation, which is going to do this. Pull up the values. So we fetch the column index at that value and we fetch the value at that value, and then we can do this. So we can do atomic add of d underscore c of RID, comma value, comma db column. Column is just column is column. Does this make sense? I copied the actual computation from the previous implementation because we still need to do atomic accesses. If I recall correctly, this upper bound has very little impact due to jumps in warp. Yeah, so this binary search implementation, right? Let me get to that. Hold up one second. I'm just trying to figure out if what we wrote is correct. So we did a binary search to identify which index in the array, in the local array we have to process by searching for the NNZ ID into that shared degree array plus chunk offset. Chunk offset is how much does this row own? Okay. And minus one because we're doing upper bound. RID equals to shared row of chunk ID plus array. So shared row is holding the thread IDs, which is the actual vertex ID that we're processing. So this gives us the row number that we are processing. Great. RPTR gives us how far in the, or where does the index of that row index, the column index or the value index of that row starts. So that is shared of RPTR plus chunk of RIDX, which is correct. Plus NNZ ID. So NNZ ID is like the current NNZ, the non-zero number that we are processing. Perfect. Minus shared degree of chunk offset plus RIDX. Yeah. So where, like, how many non-zeros were there up to this vertex that we have to subtract. Perfect. So this gives us the number of the exact row pointer that we need, which we then use to index into the column array and the values array, and then do the computation. This is almost correct. Before I fix this, let's talk about the comment in the chat. If I recall correctly, this upper bound has very little impact due to jumps in warp. Yes. So if you actually look at the implementation for this, there is a jump in here. There is sort of like a if condition, right? And different, so okay, but one thing is important. All the threads are going to run this function at the same time because warps run in lockstep. Threads in a warp run in lockstep. All the threads are going to run this function at the same time, which means they're going to run this while loop at the same time. All of them are also going to have the same length, which means that the array length that they're processing is exactly going to be the same. Every time this gets halved, so it almost has like 5 iterations of this loop. What we are loading from is the shared memory, so this is very cheap. This access is not expensive at all. It's almost like reading from a L1 cache. And then each time they sort of take one of the two branches, but then they immediately merge. It's not like they're constantly diverging. Like they diverge for a second and they immediately merge because this if condition takes two different branches and then immediately merges back again. So the next iteration, they'll all be merged again. This has divergence, but the divergence is very small. So just think of it as like what happens when things get diverged, right? They have to do one side first, and then the threads have to do the other side next, and then the threads are masked in and out. This is almost as if like all threads are doing this. Like there is no condition. It's almost as if like all threads are doing both the sides. Or, like in the worst case, all the threads are doing both the sides because half of the threads are doing the one, the other half are doing the other. That's fine. It's just like one more operation to do. It's not too bad. So in that sense, doing this binary search on shared memory locations is not expensive. This is pretty cheap. Mainly because it's happening within a warp. If it was happening across a CTA, then it's a bigger operation and it still has costs, but it's still in shared memory, so it's not too bad. But yeah, but hopefully that answers your question on why this binary search is not cheap, not expensive. Okay, so we did, I think, almost everything correct here. I haven't run it yet, so we'll figure it out, except for this length. This length is, we have put it as 32. Is this correct? We don't want to search for elements that are at the end, like because at the end we have stored these values, right? We have stored 0 and -1 and 0. The degree being 0 is fine. This doesn't contribute anything to the computation. The prefix sums just become like 1 2 3 4 and then 5 5 5 5 5, which is fine. That's good. But this value is still 0. So if a binary search goes to the very end, we are violating the binary search's property, and you might end up like processing the wrong elements. So this actually needs to be exactly where that array ends. It cannot go further than this. But the problem is it's going to be like dependent on where the array ends. So instead of like fixing this, I'm going to make this into a variable. So let's call it like int len. Okay. Len is going to be the array of that length that we have to sort of that we have to do a binary search. Most likely this is going to be 32, but we don't know exactly how much it is. So first we're going to compute where does this warp end. So let's say int warp end equals uh, thread ID minus uh, wait, hold up. We have chunk ID, right? Chunk ID gives us chunk offset, gives us the start of this. So it's going to be chunk offset. No, but we want the global ID, not just the local ID. So let's say thread ID minus lane ID. Okay, so this will tell us where does this warp begin plus 32. This will give us the end of the warp, right? So we have where does this warp end? Like where would it normally end? But if this is more than, so if say if warp end is more than num rows, like if this is actually more than our total number of rows, we're going to say warp n equals num rows, right? So if you're going past the total number of rows, then our warp n is done. And now we're going to say int len equals warp n minus thread id minus lane id. So this is exactly what we had started from. Like this and this is the same. We had added 32 to it, but then we updated it to see if it went past, and then we subtracted it back again. So this gives us the length of the actual array that we should be using. And it's the same for all the threads in the war because they all are processing the same array. I hope this makes sense. Like this small sort of computation makes sure that we don't actually go out of bounds of what we need to process. So we basically assume that we are going to start processing from we're going to process from thread ID minus lane ID. That is the beginning of that warp to the end of that warp by adding 32 to it. Then we're going to check if this goes beyond the total number of rows we have to process, which is here. If it is actually should be greater than equal to. Yeah, if it's equal, then doesn't matter. Yeah, if it's greater than num rows, then set warp n to be num rows, and if it is, and then compute the length back again by subtracting that warp n from the start of that warp. And this gives us a correct implementation of our warp balance strategy. Let's let's go over this once more quickly. So we created this shared arrays to compute the local prefix sum. We filled those arrays up with the vertices in the data that needs to be processed. We did a quick prefix sum to compute where each source and then like each row and the non-zero start. And then we figured out, like we just iterated through all the non-zeros in a collaborative way. Actually, this is wrong. This shouldn't be nz plus I. It should be plus equals 32, which is the warp size. So yeah, because each thread starts from its lane ID and then goes 32 across. That way you still have coalesced accesses. Sorry, I made a mistake here. I should have seen this before. And then we have nnz ID less than total degree plus equals to, this is perfect. This looks good, good, good. Okay. Now I'm going to insert a call to this. So running WM version threads in a war collaboratively process non-zeros in a load balanced way. Okay, I'm gonna say this is CTA size because that's what we said before. This looks correct. This looks correct. We've copied over the. Why is this here? We need this. Oh, I think we need this to make sure that the output is correct. Yeah, this is just initializing it to zeros. Right? Uh, Oh, this is copying the device version to the host version. That doesn't do anything. Oh, did we initialize the values to zero, by the way? We did not. So all the rows also have to initialize the output to zero that we're writing to. So yeah, that needs to happen here. We can also initialize it to zero. So we're going to say d underscore c of, yeah, we need to initialize the output values to be zero, which you can do beforehand. Okay, this should be good. Uh, I'm going to change this to WM, num blocks, block size, This doesn't require this. I don't know why I was passing this either because we have A, so we could get a number of A, that's fine. Perfect. Let's try compiling it. First of all, see if it even compiles. Okay. 96. Oh, it accepts in 32. Okay. Let's just make this in 32 then. Doesn't hurt. I don't know why I made it in 32. It's probably how Changwon wrote it initially. Integer conversion. Okay, 74. Cool. We have our what did I change? Yeah, I changed degree, right? Okay. Perfect. Now we have our code compiled. Let's try to run it. I have a hint this might actually give us a wrong result, but we'll get there and we'll see how it goes. Okay, so we have an illegal memory access encountered, which means we did some computation wrong and we're doing an out of bounds access. So the easiest way to fix this is to attach a debugger. First of all, we compile it with debug symbols. So we add -g, and then we do make, and we'll just figure out where the illegal memory access is. Actually, I should just comment out the other versions too. I should, because it's going to be incredibly slow if I try to do it. So let's go here. Do this. And let's change this to only do one run and no warm-up runs. So that way everything shows up immediately. Okay. So the way you run CUDA GDB is user local CUDA. I think they're using 11.4 for this one. Pin CUDA GDB. The CUDA GDB runs the same as normal GDB, so arguments and everything is the same. Great, so we have illegal memory access on this one. Let's see what the RPTR value was and why did it fail. So RPTR value was 42. That looks wrong, right? That definitely looks wrong. Okay, let's look at what the NNZ ID was. How did this even happen? Uh, what is the lane ID? Lane ID is 0. Print uh, NNZ ID. And NNZ ID is also 0. So this is like one of the first ones. Let's print RIDX that it got -1 for some reason. Okay, this is why it's doing out of bound access. Basically, it returned -1. The -1 did a lookup into the shared memory. It did a -1 lookup, and that's just off because I think this must be the chunk offset must also be 0 for this one. I'm guessing. No, it's 32. Still, it's reading a value from the previous one, and that's just wrong. Uh, let's see. Why is our RIDX -1? Let's look at our source code. Okay, this shouldn't interfere with this. This computation doesn't matter unless. That should be fine. I think this is what we missed. I think it should be less than equal to 32, right? We need to do 5 steps, not just one. Uh, 5, not 4. Sorry. Let me think about this for a second. If it's 32, no, 32 would be wrong. Sorry. It should be 16. It should go up to 16. If it was 32, then it will just send it to the same location. It's not what we want. So this is wrong. This is correct. Uh, Let me think. Total degree is receiving from the 31th lane. Everyone, perfect. If lane ID equals 31, degree equals to 0. Shared degree of chunk ID plus lane ID plus, oh wait, chunk offset plus lane ID. Yeah. Chunk offset plus lane ID plus 1 modulo 32 equals to degree. This looks correct. Okay. Yeah, we were writing at the same location. All the other values were filled with garbage. Let's see if this works. Okay, it runs, there's a mismatch. Like the values are not adding up, which is fine. We can debug that too. I think I might have forgotten to copy the values back again. Yeah, we didn't copy them back. We need the CUDA copy. But that was what that CUDA copy was for, the one I deleted. Oops, that was for to copy the value back, not to copy it before the kernel. Sorry about that. I should have kept it. CUDA copy d and h underscore c d underscore c. Sorry, folks, that was size of star h underscore c times num rows, right? Yeah, num rows, and CUDA copy device to host. What num rows? What does the main function call it? Oh, it is a dot num rows. Great. Yeah, should have kept it. Great. That is a mismatch still. This time it doesn't look correct. Let's look at our kernel again. Maybe we make a mistake. It seems like values are being skipped, right? Like some of them like just remain 0. RID equals to shared pointer of chunk offset plus RIDX is correct. Hmm. Let's turn the lights on. Hold on. Starting to rain outside, so it's getting dark inside now. Okay, let's see. What did we miss here? Let's see if all the values are wrong, actually. You know what? Let's run this properly. What? Where did the command go? Oh, I had a space in the command, so it doesn't put it in the history. You guys didn't know this. Okay, let's look at the. I think like it's skipping over some values for some reason. It should like that. Yeah, so it writes to 0, it writes to 1, and then it just doesn't put any values here for a bunch of values. I see. And then, yeah, it skips over a bunch again, it skips over a bunch again. I think a few things I forgot to do was also synchronize all the threads before we do these things. Like this needs to be initialized to, like once this writing is done, we need to make sure that threads are synced. I don't think that's the reason for this though, but it doesn't hurt to fix this. And then this all should be fine. The reason the threads need to be synchronized is you don't want some threads to still be initialized in the shared memory while others actually going to do the prefixing. This only synchronizes threads across the CTAs, but also it's useful. You don't want to like read junk values. That's the more important thing. Uh, Sync thread? Is it sync thread? Come on, what is it? Uh, CUDA sync threads. Oh, there's no space. Of course, there's no space. It's been a while. It has been a while. Come on. Okay, there's still a mismatch. That's not the reason. Uh, Lane ID equals to thread ID modulo 32. Chunk ID is thread ID x dot slash 32. Chunk offset is chunk ID into 32. That's correct. Shared memory is properly initialized. We're doing shared row of thread ID x dot x equals to thread ID. Shared RPTR is thread ID x dot row PTR of thread ID. Okay. Row P and the degree is correct too. And then we're initializing t underscore 3 of thread ID equal to 0. Perfect. And then we're doing shared, the other ones you're filling up with 0. That's great. Degree equals to shared degree of thread ID x. We're picking up our own degree that we put in. And then we are doing 1 to 32. We shuffle sync up to D. This is correct. Degree plus equals to temp. This is also correct. Sync threads. Total degree equals to get the value from the last one. Okay, shared degree of chunk offset plus lane ID plus 1 modulo 32. Is this correct? Chunk offset is where you are in the part of the shared memory that you own, plus lane ID plus 1 modulo 32, okay, equals degree. I think this is correct. And then what end equals to thread. Is this the reason? This looks correct to me. Lane ID, wait a second. Is it supposed to be lane ID? I think so. Yeah, NNZ ID equals to lane ID. NNZ ID less than total degree. NNZ ID plus equals 32. RIDX equals to binary search upper bound of shared degree plus chunk offset of len minus RID equals to shared row of chunk offset plus RIDX. Chunk offset plus RIDX. That is correct. RPTR equals to chunk offset plus RIDX plus NNZ ID minus shared degree. Maybe this should have a -1 here. Looking at the previous, it's non-zero, are we? Sum off by one error. And then column equals to a dot t columns RPTR and atomic add RID. This looks fine. This is the reason. You know what? I'm going to quickly look at the reference implementation that Changwan wrote just to make sure that I do not make a mistake in this particular part of the code. Uh, see. Oh, what did I take? Chunk ID equals thread ID exploit. Yeah, correct. The offset is also correct. Am I invoking this correctly? Warp SW. Okay, this should not be multiple with 32. This should be number of rows. I don't want too many threads, but they will all be silent anyways. That's okay. We launch more. Let's see what this does. This fix anything? Does have a mismatch. Host C size of C into non-rows non-quantity. I'm gonna quickly check if the previous versions are doing it correctly, so I did not mess up something else, just to be sure. Let's see, Fernandez. Okay, so the issue is within uh, our kernel. Okay, we'll fix this. Not a big deal. It's possible I wrote like a UN32 where suppose like there's an int32 or something and messed that up. Yeah, like for example, this one, right? I don't want to use, it shouldn't matter, but you know what? I'm paranoid that way now. Chunk offset plus NNZ ID minus shared degree of chunk plus RIDX. This looks correct. Hmm, degree. Okay, this is not the kind of issue that we had last time. Last time it wasn't running. This time we have an error. This is easier to deal with, hopefully. Not completely confused. Okay. Maybe it is this warp end issue, but how often would this show up? Only for the last one. The previous one shouldn't be wrong. Um, so I don't think that is this. I mean, one way to fix that is just change this to 32 and see if at least the previous vertices are correct. No, all our vertices are wrong. So it's not this one. It is shared degree plus chunk offset len NNZID. Basically, some of these values are just remaining untouched for some reason. Right? It's bizarre. Did I compute the thread ID correctly? It looks correct. Store the thread ID here, shared row. Is this, yeah, shared degree of chunk of surface area. Is this correct? Uh, Destination ID equals to, yes, this is correct. Total degree is in 32D, and then ZI plus equals to 32. This is thread ID minus lane. I'm looking at Changwon's reference implementation, by the way. If total size is less than width, width equals to total. This is looking fine. Width minus equals to warp in minus thread ID minus lane. Yeah, this is fine. Uh, should this be modulo 32? Yeah. Lane ID plus 1 modulo 32 plus chunk offset. Yeah, this looks fine. Shuffle sync up degree. Yeah, this is fine. T goes from 132 modulo. Did I not launch enough threads for this? Location. Okay, I'm gonna bring up the implementation that Changwan had, and we will see if this is similar to what we have. Okay. So what he has done in our implementation is he has the similar three ones, and this IDX is corresponding to the row array that we have. Degree is similar to the degree, and lock is similar to the row pointers. I'm going to put this side by side. Yeah. Uh, or if I just clone this, I can put it side by side too, right? Yeah, that's probably better. Should have it cloned. New computer though. Okay. Oh, we do already have it. Okay. Uh, Time input GPU load balance. This is the same implementation that something similar to what we have written here. Let me look down the font a little bit and let's compare the side by side. This is a more generic implementation, like the payload and everything of what needs to be done is taken as template parameters. So this is a more general implementation, but I don't think that's, I mean, that shouldn't be a reason. So thread ID is correct. We're doing thread IDs less than number of num rows. That's correct. Index equals to get element, which is basically gives us the vertex to process. In this case, it's just thread ID. This is correct. We're loading up the degree. The degree is just row pointers of thread ID plus 1 minus row pointers of thread ID. This is also correct. And then we have initialization here that's only specific for this application. Degree equals to 0. Row pointer equals to 0. He's not initializing the row pointer. I think that's okay. Uh, Only degree matters. Perfect. And then he does prefix sum. Lane equals to thread ID x dot and 31, which is the same as what we have done. Offset equals to thread ID x minus lane. I think this is like the chunk offset for us. The offset here is like the chunk offset. Okay. And then degree equals to shared. Wait a second. Okay, the degree is loaded here already. It's good. Each thread has its degree already. We just load it again. D equals to 1, D less than 32, D star equals to 2, which is the same. Shuffles up sync minus 1, degree D. Looks exactly the same actually. Oh, yes, this is a mistake. If lane is greater than equals to D, degree plus equals to 10. That's a difference. Why did we miss this? So, uh, right. So okay, when I made it on the piece of paper, I did not do anything for the lanes that were before the like we are only adding it ahead. We just skipped it for the previous ones. Right. This is causing the issue. Okay. If lane is greater than equals to degree. So when I was doing the computation on the paper, I like just skipped all the rows that were like suppose I'm doing a step of 4, I skipped all the first 3 ones because they're not adding anything from the previous ones. But that needs to happen in the code too. If you don't do this, it's going to do shuffle sync up and it's going to read a value from like the warped around thread and it's going to be all wrong. That's what happened. This is part of the reason probably. Let's try running this and see if this fixes. Not lane ID. Yeah, okay. I had the right idea in my mind. I wrote the wrong implementation. Come on. We still have a mismatch though. Right, it's all 0 now. Huh. Somehow even worse. If lane ID is greater than equals to degree, then do degree plus equals temp. Right, not degree, D. Sorry. No lane ID is gonna be greater than degree. What? Did I save it? Interesting. Still mismatching. If lane ID is greater than equals to D, degree plus equals to temp, then synchronize threads. This synchronized thread, he's putting it here. Shouldn't matter so much, but it's fine. Total degree equals to shuffle sync is 31. If lane ID equals 31, degree equals to 0. SM degree of chunk offset, which is our offset, plus lane plus 1 modulo and 31, which is the same as modulo 32, equals to degree. This is fine. And then synchronize threads. Warp end equals, this is the width. Width is the length that he's computing. This looks fine. Then I equals to lane ID, and then ZID is less than total degree, and then ZID plus equals 32. Uh, this looks correct. Shared degree plus chunk offset. Len I minus 1. This is correct already. Yeah, this is the tricky one. UNPTR RPTR. This is here. EI, which is edge ID, equals to SM lock, which is RPTR, plus ID, which is IDX, perfect, plus NNZ ID minus SM degree of chunk offset plus RIDX. That looks correct to me. And then we fetch the thing from RPTR. Is that sync thread causing the issue? Couldn't be, right? What is going wrong here? Everything is just zero. Why is everything zero? If you guys see something, please let me know. I am confused now. Once again, lane ID is greater than equals to d degree plus equals to temp. Hmm. Yeah, the other issue with like debugging code like this is like you can't just look at those prefix sums and you can't just look at those values because it's just too large. What we could do is we could do a fewer number of non-zeros and see if that is easy to debug. So we could step through the code and figure it out. Yeah, let's do that. So okay, the way I'm gonna do that. Oh, wait, no way! I not launched the kernel. Come on, I had the kernel commented out. Jeez. And that's why it was all zero zero zeros. I'm an idiot. I was when I was debugging the if it's running correctly, I had commented it out and I did not uncomment it again. And there we go. Now it runs correctly. Sorry about that. Okay, now I'm going to clean this up again. So the only mistake we had was that when doing the prefix sum, I did not have this condition here. If lane ID is greater than equals to D, this was making it so that they were adding values from the end of the row again, which completely messes up our prefix sum. So this is important. Remember, this is important. And then everything else I think seems to be correct now. So yeah, I'm going to enable all the versions and we can see the execution time side by side. I'm also going to run it for enough number of iterations so we get a complete view of what's happening. All right, let's look at this now. Okay, yeah, so we are compiling it with debug symbols now, so it's obviously going to run slower, but I'll recompile it without the debug symbols, and then we should get our correct execution time. Sorry, this took longer than it should have. That's how debugging goes. Okay, so we can see now that this execution with the warp m is actually slower than the co-warp execution. It's still faster than the basic implementation we had where we did the load balance within by assigning one thread to each row, and then we did our co-warp strategy, which did some like a lot better than that. And now we have actually gone down on the performance a little bit. So why did this happen? Like our load balance strategy is supposed to do better than the previous one, right? Let's quickly attach the visual profiler and see what is like. Are we at least doing the memory accesses correctly like we were before? And we can compare the two kernels side by side. That will be easier. I'm also going to bring this to the middle, and then hopefully my display capture filter works properly. Yeah, good enough. Okay, so let's look at the second kernel that so SPMV WM and coarp, right? Let's just go at the coarp one again. Let's just to see how it was performing before. I should have changed the kernel to run only once instead of running these many times, but that's fine. Examine individual kernels. Let's look at coarp first. Let's look at global memory access patterns. Yeah, so if we look at the global memory access patterns, we see that there are three global memory accesses, right? One is to load the destination or the column index. The second is to load the value of that non-zero, and the third is to do a random access into the into the dense vector to get the value for doing the addition. And then the final is the store. The store is pretty good. The store is actually where is the store? Oh, it's an atomic add now. So probably show, yeah, here. Wait, we're looking at the co-op one. Anyway, so we had fixed these two global memory accesses. They are much better now than before. Like the ideal is 2.1. We have 2.5. Ideal is 2.1, 2.5. That's good enough. That's like it does happen that towards the end, some of the threads in a warp actually don't do anything, so that's not ideal. But anyway, this is good. This was our previous one. Let's go back to our other kernel. Let's look at the core the WM1 that we wrote and see how well it performed. So the way to do that is go here, analysis, examine individual kernels. This time we're going to look at the co-op one. No, sorry, WM1. And let's look at the memory accesses here. So in this one too, these two are not as bad. So it says the global loads, the ideal transactions would have been 3.9, we get 4.8. And this one is 3.8 should be, it gives us 4.6. This is still bad, which is expected because when you're doing random accesses with those column IDs, you're fetching values from all the way in the vector. It could be bad. So the global memory accesses are worse than before, but not as bad. So at least that problem we haven't faced now. I mean, we haven't made it worse than before. Let's look at divergence execution. How much divergence do we have in this one? And we'll also look at the divergence execution in the previous one. So there is a divergence. There is a divergence of 5.3%, which is happening again at the end of the loop. So they're just running different at the beginning of the loop and the end of the loop. There's a lot of divergence, and that's happening because threads are basically doing different amount of work. Let's look at the divergence in the co-warp strategy one. And that one had two different hotspots, but they were like, yeah, they're not as bad as this one. So there's a like we these two strategies are very close in the implementation. Like we haven't created any major issues in terms of global memory accesses or anything like that. We are still doing so that okay. Usually divergence and global memory accesses tells you about like hotspots, like the points in the kernel where you're doing more work than you should, or like you're wasting utilization and so on. But if you end up doing more work by itself, that doesn't show up on this profiler, right? Because if you just have more instructions, that has a cost, and that's part of the sometimes where it shows up. So one way to do that is look at PC sampling. Let's just look at how much time is spent in the two kernels doing different things. So PC sampling, it doesn't have information. They changed this. Some kind of latency. I just want to see which instruction is taking how much time. Insufficient kernel latency data. eGPU term the user doesn't have sufficient permission to profile on target device. Oh, it's not letting me gather all the information in eGPU perm. The user does not have the Do I need to enable it for all users or should I just run it as root? Will it even run it as root? Probably not. But I'm just gonna. It's okay. I don't think we need the PC sampling, but the idea is we are end up we spent a bunch of these instructions in the beginning trying to do the load balance to figure out how many threads like need to do how much work, and that has a cost. Now that cost is not always justified. It depends on like what we are comparing against, right? If there isn't enough load imbalance with the initial strategy that we had, adding this extra cost for doing the load balance doesn't help so much, but it still has a fixed amount of cost, and that's where it goes wrong. So why did we even bother implementing this load balance strategy? The answer actually is pretty simple. The kernel we are implementing, the SPMV kernel, actually we didn't need to do all these things to get the best performance. Let's actually save the changes and look at it. So what are we essentially doing? We are doing a load balance on the degree of the vertices, right? And then the way we are doing that is we're first loading the degree of the vertices into the shared memory. Then we are doing a prefix sum on those degrees, and then we're binary searching in them. If you look at this carefully, this row pointers array is already the prefix sum of all the vertices. Sorry, I should get back to the normal size. If you look at this row pointers array that the graph has or the matrix has, that's already a prefix sum of all the edges that you have to process. So why shouldn't we just use this? Like we can just do a binary search on this one and know where to start, which vertex you have to process. The reason this one works is because we are doing SPMV. What that means is we are we are processing all the rows in the matrix. Let me actually draw the screen again, and I'll explain why this is not as good of a strategy. And we will improve this. We will make it faster in the next step. Okay. How do I bring up my Zoom? But I just wanted to show what the warp balance strategy is and how you actually approach trying to balance workload across threads. It has applications, trust me, I'm not making this up. Okay, so what we have done for this implementation is SPMV, right? So we have a matrix, it has a bunch of rows, and it has a vector that we are multiplying with, and then we have an output vector. We are multiplying each of these rows by this column and then storing the values here, right? This is SPMV. But what if we were not doing SPMV? Suppose we were doing SPM SPV, which is when I'm multiplying a sparse matrix with a sparse vector. So that's SPM SPV. Or rather I want to say do this. I want to multiply this row with this column, store it here, and that directly suppose skip to this one. Like I don't want to multiply all the rows. I want to do like selectively some rows and produce output only for these elements. What happens in that case? It's still a sparse kernel. It still requires different number of non-zeros to be processed, but we don't have that row pointer giving us the prefix sum anymore. Now we only need to do a prefix sum for these elements, not like hop across them. We don't have to take the degree of these vertices included in the prefix sum. So we don't necessarily have that available. And that is where this load balance strategy WM shines really well. Like if you're at SPM, SPV, if you're doing only a certain set of values, then this one becomes very useful because now you actually balance the load correctly across the threads. If you look at our previous strategy of doing the warp method mapping, the co-warp stuff, even that wouldn't work as well with this one. Because I mean you still like leaving some of the non-zeros in the middle, and that's where this starts to fail. So why did we write this warp mapping one? Because it is useful for interesting in my discrete access is always a pain. Yeah, I mean it's not just about memory accesses, it's also about you don't have in one array all the non-zeros stored. Like if you look at our CSR data structure, what does it look like? We have the row pointers, we have the column pointers, and we have the value pointers, and we are essentially just going through all these values and doing the whole computation. So this is like I'm accessing these values one by one and just like doing the computation. But when you have when you're doing SPM SPV, you're saying I don't want to go through all the rows, I want to like do few of these rows. So in that case I'll basically do this, and then I'll do this, and I'll do this, and I'll do this. I'm skipping values in the middle, and that's where like load balance becomes more useful. because now you don't already have a prefix sum of all the values. If I was writing SPMV, I would actually not use this load balance strategy because it's doing more work to do the computation that I already have. Like the prefix sum that I need is already there in the array for SPMV. It's more useful when you're doing SPM SPV. So what's the right way to do SPMV? Like why should I directly do a prefix sum on all these elements? Yes, if we do a prefix sum directly on those like sorry, not prefix sum. If I do a binary search directly on these values, like these column IDs, and get the source IDs, that's actually going to give us a better performance. But I'm going to skip that one for this discussion. What I'm going to do is directly go to the next strategy, which is basically called a edge only strategy, or which basically says I'm going to, it's a specialized load balance strategy when you have this kind of a like going through all the non-zeros. And before I implement it, I'm going to explain it. So normally what do we have? We have a CSR array, right? Which has row pointers. So let's draw it neatly this time. So these are row pointers, these are column IDs, and these are values, right? If I want to do the thing that I just described, which is just do a each thread will do a binary search on these threads, figure out which source vertex to. So these are basically pointers that go into this array, right? Like they tell us where does this row start and so on. So if I do a sort of first I find where I start. So like total number of elements is the total number of total number of elements in this column. I go and each thread figures out I'm going to start here, I'm going to start here, I'm going to start here, because that's like equally dividing all the work. And then they do a binary search in this one to figure out in this array to figure out where they start in the so they do a binary search in this row PTRs to figure out where they start, because this is storing in an ascending order. Like this is almost a prefix sum of degrees. It is in fact the prefix sum of degrees, not almost. It's exactly the prefix sum of the degrees. And then they do this binary search and they figure out where to start. But here's the thing. Do we really need to do this binary search every time? Imagine a case, suppose we're doing this SPMV computation 100 times, like we are doing. In fact, this is very common. When you do SPMV, like for applications like PageRank, or if like some other applications, you actually multiply the same matrix over and over again with different vectors. Think of like machine learning applications. You have some matrix as part of the weight matrix, and then you have the data coming in. When you're doing inference, you're not really changing your matrix at all. You're just changing the vector, the data that you're operating on. So we are actually going to do the same matrix vector multiplication over and over again. So how can we sort of take advantage of this? Can we sort of like make this whole operation of load balancing cheaper? That's what. So the way we do that is there's this like we do a pre-processing optimization. So the pre-processing optimization is we actually convert these two this representation into a representation that's more suitable for SPMV, which is we call the COO. So this is CSR. We're going to use another representation called COO. COO is the simplest sparse representation that you can think of. It essentially just has three arrays. One is the row array, one is the column array, and one is the values array. Okay, the row array, it's basically for each non-zero in the matrix, we store a three tuple. We store what the rows ID is, what the column ID is, and what the value is. So it's basically, if you have 100 non-zeros, it just has three arrays of 100 size, and each element stores that non-zero's row, like basically which row is that non-zero in, which column is that non-zero in, basically the coordinate of that non-zero, and the value of that non-zero. It's not stored as this compressed row format. We are storing it as basically COO, which is called the coordinate format. So it just stores the coordinates of those non-zero and the non-zero itself. Now, what's the benefit of this kind of a representation? Load balancing is incredibly cheap on this. How do you load balance this? You just split the array. So suppose you have 4 threads, you split the array into 4 things, and now you iterate through your chunk, and you now know where to start and where to end. You basically know my work is to process from this part to this part and this part to this part, and for each of them you know the rows. Even if this row changes here, like R1 becomes R2, you know this because those row values are stored. Like for each non-zero, the rows and the column values are stored. So that way you don't actually have to do a binary search to figure out where to start. You just like literally take the pairs of coordinates, split them equally among all threads, and do it. Now, can we apply this to SPM, SPV? No, because in SPM SPV, we're not doing all the non-zeros, which means there'll be some of those values that we'll skip. We won't be processing those, right? So if we just equally divide these arrays and process them on different threads, they will end up doing different amount of work. So this sort of strategy is very, very useful for SPMV. So what I'm going to do now is actually I'm going to implement this. And the first step to implement this is to first implement this new format, or like create this new format representation in memory. And then we will use that to sort of actually compute it. So I'm going to stop sharing. Oh, this one. Uh, and let's do stop share here too. Okay, so what's the first thing we have to do? We now have the CSR implementation. We have to create the COO implementation from it. So what I'm going to do now is I'm actually just going to change the matrix. Hold up, this is showing up still for some reason. How do I quit this? Okay, so I'm going to add another array called the row array. UN32 UN32T star H underscore rows, and I'm going to say UN32T star D underscore rows. So this is just going to like store the rows and destination. Array to store the source of each non-zero, or row of each non-zero. Let's change this to column of each non-zero. Right? So we're still going to keep the row pointers, but we won't be using them. We'll just directly use this row and the arrays. And how do we populate this? So once we load the row pointers, we just have to iterate. We need to allocate memory for this one too. So I'm just going to say this is host first. So we're going to compute it on host and then copy it into our destination. So this is fine. Num values. Rows. So we have allocated that. Now we just need to fill it up. So easy way to fill this up. What do we have to do? For each row we know how many like times does that source appear, right? We know, so in the compressed format we basically have for each row where does its non-zero start and end, which means we know the degree of each row, or how many number of non-zeros are there in that row. We just need to we just need to paste that same row ID that many times in this. So I'm just going to write a simple for loop which goes int rid equals to 0, rid is less than g dot num rows, rid plus plus. Okay, and then what I'm going to do is I'm going to maintain a running counter. So I'm going to say uint32t counter equals 0, and then I'm going to just paste this value that many times. So for I int idx equals to, actually we don't need a counter, so I could just simply say for each of the row we can say for int cidx equals to g dot row ptrs, but the host version of that, host row ptrs of rid, cidx is less than g dot h underscore row ptrs of rid plus 1, cidx plus plus. Okay, and for those locations I'm going to simply say g dot h underscore rows of cidx equals to rid. So I'm just going to copy, like just paste that row ID, like how many times ever it appears in the edges. So I have the COO representation now. And then I'm going to allocate the same memory for the GPU. So d underscore rows, size of d underscore rows, and then I'm just going to CUDA copy it. So just like I copied the columns, I'm also going to copy the rows on the host rows. Okay, and then that's about it. We just have copied we just have created this new representation. I'm just going to quickly run make and make sure that everything else is still running fine, nothing broke. Um, and we can implement our edge only strategy. Oops, sorry. Never mind. Okay, great. Everything is running fine. We have our code working. Okay, now let's implement our edge only strategy. So this one is very simple, by the way. We just have to divide all the work and start processing it. So this is the simplest implementation you can think of. Doesn't have all this stuff about load balancing. I'll later show you how like SPM, SPV, if we do it this way versus the other way, how well this WM strategy performs. There are other load balance strategies, by the way. Our paper has three more other load balance strategy. So there is the CM load balance strategy, which is the same as like similar to WM, but instead of trying to do a load balance within the warp, we do a load balance across the whole CTA. And then we have TWC, which basically tries to address this problem of like different threads have different number of non-zeros, different rows have different number of non-zeros, which means they need to have different strategies. So we first segregate the rows based on the degree that they have, and then we apply different strategies to them. So some do like load balancing over edges. If the degree is too small, we just like to assign them to different vertices. If the degree is to different threads, if the degree is too large, we apply it to the whole CTA, and the middle ones get the warp sort of treatment. And then the other one we have is called the TWCE, which is basically a similar version as TWC, but instead of segregating the vertices, the rows themselves, it actually segregates the non-zeros from the rows. So it says, okay, from this particular row, I'm going to take chunks of non-zeros that are like multiples of the block size and process them as blocks. Then the remaining ones I'm going to process as multiples of warps, and the even remaining one I'm going to process them as like individual threads. And that actually improves performance quite a lot. That's the strategy that we have in our paper that we sort of introduced, and it improves performance across the board. But anyway, we'll get to that later. I'm going to just implement this edge only strategy. So I'm just going to call it EO. Everything is exactly the same. The first thing I need is the thread ID. Uh, okay. Now for each thread, we're going to start the actual loop. There's really not much to be done. So let's say int uh, NNZ ID equals thread ID. We all start from our own thread ID, and we want to maintain coalesced accesses if we can. So that's why I'm doing the co-op strategy kind of thing. So NNZ ID equals to thread ID. NNZ ID is less than g dot num values. NNZ ID plus equals uh, threads equals block dim.x multiplied by grid dim.x. So grid dim.x gives us the size of the grid, by the way. So how many number of blocks there are. This is gives us a total number of threads. So I'm just going to say plus equals to num threads. Okay, so we are hopping over the entire thing at the same time. And then within this, I'm just going to do int RID equals, how do we do it? We just do g dot d underscore rows of NNZID. How do we get the column ID? We just do g dot d of columns of NNZID. And then how do we get the values? Um, That's it. Because our array, our data structure simply stores the four values in different arrays for each non-zero, we can just fetch them like this. And now we still need to do atomic access because we need to do atomic accesses because multiple threads are still modifying the same non-zero. So we need an atomic access here. So this d of c of RID value, this is good. The only thing we need to make sure is values are initialized properly. They should be initialized to zero, right? So unfortunately, there is no correct way to do that here because these values, because we are launching uh, a bunch of threads and we don't have sort of threads equal to number of, actually maybe we could do that. So we could launch, uh, that would be wasteful. So what I'm going to do is I'm going to simply write a separate kernel that initializes all the values to zero. That's like spmv underscore eo underscore init, uh, which is the simplest way to do this. So floats are t underscore p dot t underscore c. We don't need the numbers. We need the And this is an easy implementation. All we do is if thread ID is less than num rows, then d underscore c of thread ID equals to 0. Right? Just initialize the values in a different kernel. That way we don't have to think about it here. Okay, and this one just does a aggregation of the values. Okay, let's call this kernel. I think this should be easy. Or I'm just going to remove this. So running EO version threads all threads collaboratively process all non-zeros. Are you writing for the GPU? Yeah, so we okay. Let me write this code and then I'll brief you on what's happening. Process all non-zeros in COO format. Yeah. So we this is since you're new here, this is a stream. This episode is about optimizing sparse computations for GPUs. So I'm currently writing optimized versions for SPMV, which is sparse matrix dense vector multiplication for GPUs. And it's hard because sparse computations usually have irregular memory accesses and have irregular amount of work to do, which makes it really hard to map it to GPUs. And then in the past, we have looked at different load balance strategies before, and now we are looking at a format change that makes this easier. So we are implementing the COO format and see how that improves our performance. So yeah. Okay, I'm going to change this SPMV to say EO underscore init first. You need to initialize the memory. And then I'm going to do the actual SPMV underscore EO. We'll set the num blocks in the block size correctly later. So usually this is done with number of rows, that's fine. But what I'm going to do is for the second, actually, let's move this computation inside. So for the first one, we want the block size to be like launch one thread for each row. But for the second one, we are actually going to set block size equals to CTA size. And we want to launch a fixed number of threads. And then num blocks equals to like how many ever SMs we have. So I'm going to say, actually, we can say 160. So I'm going to launch like 160 times CTSIs. We just launch a fixed number of threads, and those threads will collaboratively process all the non-zeros. Let's see if this runs correctly or even compiles correctly first. G and column 123. Not G, it's A. And then these are all A. Column is undefined, CID is declared but never reference. 128. I should just make an alias for MA. I make the same mistake all the time. Okay, SPMV data. Okay, let's see if this runs correctly first, and then can debug it. Okay, it's taking too long. Got stuck or something. Hmm. Num thread is blocked dim.x, create dim.x. This is fine. This is all. Oops. Did not launch the kernel correctly. Okay, let's just comment this out for a bit and see how does it still take long to run. Okay, this is not gonna match, that's fine. But let's add a return zero over here. I want to make sure it runs. Okay, it is running, and that initialization is happening. It's not too expensive. Numblocks equals to 160. Actually, I should maybe make it 80. You know what? There's something up. Uh, SPMV right? Yeah, so you're doing thread ID equals to this, just NNZ ID equals to thread ID, NNZ ID is less than a dot number of values, NNZ ID plus equals to num threads. This should be correct. You know what? Let's just wait for it. Let's see what happens. Does it finish or does it get stuck? Did finish, and it took insanely long. Something is wrong on this then. Uh, okay, did the values at least match? Again, you know what I'm gonna do? I'm gonna change this to be no warm up and just do one iteration and make sure that, oops, uh, let's do one iteration, no warm up, and uh, and let's make sure that the results are correct, right? It's possible that we wrote some wrong code. It's not supposed to run this slow. It should be. Okay, yeah, it's doing something wrong. Num blocks, block size, A, DPTC, A num rows. By the way, when you launch two different threads, when they run after each other, there's a synchronization between them. They don't run at the same time. So yeah, the init ends and then EO starts, so that should be fine. Uh, you can change this to be, it shouldn't matter, CTA size times 80 because that's the number of threads we're launching. Uh, Plus number equals to thread and then z equals to thread ID is totally fine. We're just strip mining uh, non-zeros. All of them are zeros. Nothing is being touched. Did I enable the kernel again? Yeah, I did. Maybe the kernel launch failed. You know what? Let's Pura cheating. Oh, in Pura GDP. We're just gonna check if it runs without any errors, so we don't need to compile it with debug symbols for now. Oh, it's possible that we made a mistake in the data processing part, and that's probably causing this. Yeah, that's maybe one of the reasons. Okay, so it runs correctly without any out of bound accesses or anything like that. Let's look at this. Did I make a mistake here? For each row, I'm starting from row PTRs of RID. Wait, row PTRs is loaded, right? Oh, of course. I did this before even loading anything. There we go. Yeah. So I was copying the values before the row matrix had been loaded. It was all zero, 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 zeros. Makes sense. Not even zeros. It was some garbage value. I'm surprised it even ran. Okay, let's see what happens now. Okay, this time it's running, but it has wrong values. Okay, so I fill up the row values with the RIDs and then I'm copying it to this. This is a good start. Grid string.x. Okay, this looks correct. So RID equals to a dot d rows, d columns, d. Oh, obviously. Okay, this is the mistake. I instead of loading the values, I was loading the columns and I was storing the columns in the sum. There we go. It ran this time, which is great. Let's run it. It's still not as fast. It's still slow. So yeah, we try to do the COO format, and it's still not giving us as good of a performance as before. So what happened here? Let's attach the visual profiler and see what we did wrong. So the EO init kernel, that's not taking too much time. It's literally like running in 0.1% of the execution time, because the reason it runs very fast is because it's only running once per each row instead of running once per each non-zero. So that the amount of work it does is very, very low. So what happens to this kernel? Why is this kernel running this slow? It's very similar to the WM1 version, by the way. So like in terms of execution time, it's pretty similar. So let's look at obviously global memory accesses first, because those are our usual culprits when it comes to sparse computations. You have indirect accesses everywhere, and we can see that this is the same. Like we are in fact our accesses are even more coalesced now. The two accesses that sort of uh, that load the value from the column and the row and the value array in this case, they are so tightly now that like they're as efficient as they can be. So ideal access is 4 and we're getting 4 accesses. It's the perfect. The only issue is this main load, this load that takes the column index and indexes into the dense vector and gives us the value. This is literally the problem right now. Like if you look at the the whole kernel, it is just this. Like there is nothing that can go wrong anymore. Like we just have 10 lines of the kernel, it's loading some values and it's going wrong. The sort of difference between the previous kernel and this one is still loading more values, because now we have to read this entire other array called the rows array, which wasn't there before. So that's a trade-off actually. Like we made our load balance better, we made our global memory accesses better. What we ended up losing on was the we have to load more data now, which is using the memory bandwidth more. So there's let's also look at this GPU usage. Let's see if we have utilized the GPU completely. If there's more sort of things to squeeze out of it, we could actually squeeze out of it. So saying some individual kernels. Wait, why doesn't it show for EO? Show utilization. Let's look at the utilization for this kernel. For EO, right? The data needed is not enough. Following concept. Hmm. So the following kernels are ordered by optimization importance based on the execution time and achieved occupancy. So it's not showing me the exact occupancy number, but what it's saying is it has the least occupancy of all the other implementations. Okay, SPMV, the basic version is obviously very slow. We understand that because we just didn't do any load balance. The second SPMV EO, it's saying is the next thing you should optimize. So it is as bad as WM when it comes to load balance. So that's what we should focus our optimization on. The idea is we don't have complete occupancy still. Because you have more sort of memory accesses to do now, and those memory accesses are stalling the processor more, and your threads have to wait for some execution time. What we could do is trying to launch more thread. Let's see if that improves our performance even slightly. That's usually the first thing to look at. Like if your occupancy is not enough, can we add more threads? Does adding more threads improve occupancy? It's not a linear relationship. Like at some point it's gonna stop being useful, so you don't want to like increase your threads unnecessarily. But okay, it made it worse, so that's not worth doing. This is something we have to tune. Like we could also try fewer and see if we are able to get a better balance out of it. This is a sort of a dark art. This is hard to guess. You have to try out different things. There we go. It's slightly better than before now. It's not as good as our co-op version, but it's almost there. Like that was 490 milliseconds, is 438 milliseconds. It's better than the WM strategy. Let's try even another change. Let's try to run 1024 threads per block. That could like it's just tweaking the kernel launch parameters to figure out if what's the optimum for this kernel. Not as good. So launching more threads do not help here. How about if we reduce the number of threads per block even further, like launch even less threads and see how well it performs. Because launching more threads also requires some cost in the hardware and you can trade that off. Okay, this made it worse because now you don't have as much compute available. We could try this, which would further balance it out. I think that's the least we can go. So I'm gonna stick with 512 and I'm gonna stick with 80. This seems like the fastest we get out of this kernel. So uh, yeah, let's make peace with the fact that this is how fast this one is going to run and focus on the next optimization. Okay, so 539, it's not as bad. Like it's 490, 539, it's somewhere in the middle. Again, depending on your graph data set, the co-op one might not work as fast because it depends on the number of non-zeros you have, how are the non-zero distributed. These different things matter for different things. But okay, so if we go back to the visual profiler, we see that all our implementations are suffering from this one random access issue. When we random access into the dense vector, that's where we're losing a lot of memory accesses. So can we do something about it? Like that seems like something we should focus our efforts on because it's common for all the implementations we have so far. Let's go back to the whiteboard and let's try to see first of all why it comes up and how can we fix it. I actually have slides for this from a while ago, but I think I'll explain it on the whiteboard. That might be better. Uh, okay, let me share my Zoom again. All right. Going to move this here. Okay, so what is SPMV, right? Okay, so we have this matrix we have rows in there, the same figure over and over again, and then we have this dense vector. Now let's zoom into this dense vector. This dense vector is this, like, it's a big dense vector, right? It has 4.8 million entries. It's not a small vector. It's not going to fit into any of your caches. Now what happens here? Every time I go through a particular row, like I'm streaming through these non-zeros, right? Which means I'm going through these non-zeros one by one in order, right? I'm basically using the column index, like basically this value, the index of the column, to index into this row. So like I take this element and multiply it with this element, right? Normally when you do matrix multiplication, you multiply each element by its next one. But because many of them are non-zeros, we just hop through them. We just like take an element, index it to this array and multiply it and write it back to this array. For that particular row number. Now this is what we call a random access. Like because these values are all scattered in the range, they actually end up touching different values. Which means we are constantly reaching into this array and reading different values of this array. Which is where now what happens is the GPU also has a cache. This whole array of 4.8 million entries with floating point values is not fitting in the cache. This is causing, every time you read something, it sort of causes a cache miss. You have to bring in more data, and then that goes to global memory accesses, which is slow, and everything is screwed. What if we had some strategy by which we could make sure that at a time we are only accessing a part of the array? So that's basically like cache blocking or tiling, that as we call it. So suppose I say at the beginning, I'm only going to restrict my accesses to this first 20,000 elements of the array. Let's say, yeah, cache oblivious would be really nice, but this one is not cache oblivious. This one is more, we are going to do it in a cache, like we're going to look at the cache sizes and do this blocking. The other way to do it is more like just tune the parameters and see which one works best. But for this one, we'll just do some math and figure out what the right sizes is. But what I'm doing right now is I'm going to say, hey, you have this whole array. I'm going to cut it into small chunks. And at a time, I'm only going to cut through, like touch some of these values. What that means is, now when I'm iterating through these non-zeros, I have to skip over some non-zeros. Like some of the non-zeros which are like going deeper into the array, like further part of this. So suppose I'm doing this part. I'm going to skip those non-zeros that are here and come back to them later. Then I'm going to do this and this and this. What this means is I'm essentially partitioning my matrix into submatrices. Like I'm going to call this submatrix 1. I'm going to call this submatrix 2. Let's see, submatrix 3 and submatrix 4, right? Submatrix 4 is going to touch this part. Submatrix 3 is going to touch this part of the array. So we have partitioned our sparse vector and we have partitioned our dense vector and sparse matrix. And now what we're going to do is, while iterating, I'm going to iterate through the non-zeros in the yellow part first, which will only touch this part of the vector. Then I'm going to move on to the purple part that will only touch this part. Then to the orange part that's only going to touch this part, and this and so on. What this means is for all the rows, now the first time I bring this data into the cache line, it's going to be used over and over again. So that way I don't have to like invalidate my cache, bring more stuff in, and then again invalidate and so on. And this should improve our performance. In fact, this should improve our the memory accesses that we were suffering from, the random access into the vector. Yeah, hot cache line. We basically go through each amount of data that fits into the cache one by one instead of like going all over the place. So the first thing we need to do is to sort of partition this matrix. Now, when I say partition the matrix, we usually mean like cut the matrix up into smaller pieces, right? That's essentially what we're going to do. We're going to like sort of say, I'm going to rearrange the nons, since we already have it in this COO format. I'm going to say, let's just rearrange these in a way that like, let's just rearrange them so that different the yellow part first, the purple part next, the orange part next, and the cyan part at the very end. So we're just in the same array, we're just going to rearrange those vertices and then iterate to them, and that should improve our performance. I'm just going to quickly stop sharing, and then we can start implementing it. Stop share. Okay. Give me a quick second. I'm going to put this to the side. Okay, it's okay. So this is also a pre-processing optimization, by the way, because just like COO, where we create a new format, in this one we are pre-partitioning the matrix so that when we are doing the operations, we will have good locality on those accesses. So it's it's also a pre-processing, and it only makes sense because the partitioning also has a cost. It only makes sense to do this if you're going to do the same SPMV over and over again, with a different vector, obviously. But if you're using the same matrix again and again, it's beneficial to do this optimization. So you can like amortize the cost of actually partitioning your accesses. Okay, so give me 1 second. Okay, so what we're going to do is we're going to first partition the graph into multiple buckets, sort of. Uh, So let's do this pre-processing optimization. We can reuse the same arrays where the values are stored. We just have to also store where each of the sub matrices start. So what I'm going to do now is actually going to make a uh, the lower matrix. I'm going to give it a parameter called block size. Okay, and I'm going to give it a default value of say -1. And if it's -1, which means we don't want blocking. If we have a value, then we want that many actually blocks of that many size. That's the way we're going to read this. So okay, we have allocated the host arrays, we have read the values, we have created the ECs. Now what I'm going to do is I'm going to say if block size. Did I say block size or what's the variable name? Block size, yeah. If block size equals not equals -1, then we are going to do the rearranging of the vertices. So what I'm going to do now for this one is I'll need another array to store where the buckets or the bins are. I'm just going to call them buckets. So I'm going to say array to store bucket offsets, or bins, you can call them whatever you want. So let's say h underscore bin offsets and UN32T uh, D underscore bin offsets. We need it on the hosts and the thing both, so it's unfortunately necessary. Okay, so for each bin, we're going to separate the non-zeros into the same array, just offsets into them. Okay, what I'm going to do for it locally though is I'm going to allocate a bunch of like copies of those array where we can fill them up. So we don't need the row pointers. We just need the columns and the rows. So we are not using CSR. We are doing blocking on COO. So this can be like this. I'm just going to call this uh, uh, UN32T star, UN32T star. Okay. Okay. So now what we're going to do is we're actually going to iterate through the whole thing in chunks of like this block size. So for int block ID equals 0. Okay, and how many block IDs do we need? Block ID times block size is less than a dot num rows. So we're going to go on till block ID times block, as long as block ID times block size is less than num rows. One more, not, but like, yeah, we need it to be one more. So, uh, because what will happen is we're doing it in chunks. Eventually, we don't want to miss anything. So we're going to say block ID -1 times block size less than numbers. And this is fine. So in block ID equals to 0, block, actually, You can just do this remaining blocks afterward. It's okay. Let's just do it this way. Yeah, so till block ID times block size is less than number of rows, I'm going to say block ID plus plus. Okay, and now I'm going to say what is the start and end of this block. So let's compute that. So u in, these are the offset into the vector, by the way. So u in 32t blocks underscore start equals to block ID times block size, right? And then we're going to say u in 32t block n equals to block ID, ID times block size plus 1, right? The end of the next, beginning of the next block is the end of this one. Okay. So now we have the start and end of the two blocks. Sorry, let me fix this. Okay, yeah. And now we're gonna go through all the non-zeros and see which ones fall into this category and put them into the array. So I'm gonna say for int u in 32t let's say nnz id equals 0, nnz id is less than uh, nnz id is less than a dot num values nnz id plus plus. Okay, and now I'm gonna say if nnz id is no, let's say the column destination. So if uh, g dot host underscore columns of nnz id is 32t column id equals g dot h underscore columns of nnz id. I'm going to say if the column id is greater than equal to block start and column id is less than block end, which means it belongs to this current block that we are processing, then and we need a counter for this. So we need a global counter. So you in 32 count CTR equals to 0. You need to write it down to the CTR. So this whole goes back into the new one. So h underscore columns. Let's do with rows first. H underscore rows of column ID equals to G dot H underscore rows of NNZ ID. Not column ID, it should be CTR, right? Yeah, CTR. And then we're going to append the next one. So H columns of CTR equals to G dot H underscore columns of CTR. And then we're going to say H underscore values of CTR equals, what did I call it? F. One type g dot h underscore values of CTR. Okay, and then I'm going to do CTR plus plus. So we have appended the value to the thing, and once we are done with this block, we're going to store this at the start of the block. So actually, at the beginning of the block, we can just store it. So we can say, what is it called? Bucket offsets or block offsets? H underscore bin offsets and D underscore bin offsets. This needs to be allocated, by the way, first. So, but we don't know the size of the blocks. Well, we can compute it. So, int num underscore blocks equals a dot num underscore rows plus block size minus 1. You remember the trick for doing the ceiling of a value? That's what we are doing now. A dot, no, just block size. So, and now we can actually just change this. We don't need this whole multiplication thing. We can just do block ID is less than num blocks because we are computing the number of blocks. Okay, and then block ID plus plus. Great. And now we can actually allocate the size for this. So you in g dot h underscore bin offsets we'll need one more so that we can store the end. So it's like almost like CSR. So this is going to be h underscore bin offsets equals to new un32t of num underscore blocks plus one. Right now we uh, have the offsets, uh, and now we can store this value here. So we're going to store the. We need the beginning. Actually, we just need the ends. We don't need that plus one. Sorry. We just need to store the beginning. Because the first one literally starts from zero. So why do we need to store the first one? Yeah, the num blocks can just be here. And then at the end of it, we can just store uh, g dot h underscore bin offsets of block underscore id equals to ctr. So we are storing where each block ends into this array. And this is a slow process. Now we're going through like basically the graph multiple number of times, the whole non-zeros multiple number of times, but this is a pre-processing optimization. We're doing this ahead of time. You're not counting this execution time. In fact, if we want to count this execution time and amortize it, we could actually implement this also on the GPU in a very performant way, and then we could show that including this transformation, it doesn't cost too much. But I'm going to skip that for now. We are assuming that the computation runs like thousands of times, and that's why this cost is not too much. And also sometimes you can just load the graph in this format. You can like store your graph already in a blocked way. So you don't need to do all those things on the fly. Okay, so we have created our offsets, but now what we need to do is we need to just patch the arrays back again. So I'm going to delete the old g dot h underscore rows. I'm going to delete the old g dot h underscore columns. I'm going to delete the g dot h underscore values. Right? We don't need those anymore. Also, this value should be float. And now I'm going to just assign them. So I'm going to say g dot h underscore rows is equals to h underscore rows. G dot h underscore columns equals to h underscore columns, and g dot h underscore values equals to h underscore values. Perfect. So now our sort of arrays have been done, and I'm also going to do bin offsets already done. We actually don't need these bin offsets on the device. We only need it on the host, because while launching the parameters, we can take care of this. So we don't need it on the on the device. And yeah, so we have blocked our arrays now. The copying and everything should be great. But wait, this is going to screw up the computations for others. Oops, so what needs to be done for this? Yeah, we're using the same graph for two different computations, so I guess I can't do this. I'm gonna have to store them separately. It's okay, I'll just store them separately. I'm gonna say h underscore rows underscore blocked, and then I'll just use different arrays for the two, because we are also doing other computations with it. We're not just doing one computation, so it's like, this means I need blocked versions for all these two. But these will be filled only if we do the blocking optimization. So hopefully it's not too bad. I type, what is happening? Had enough coffee. Also, is this correct? Oh, I'm storing values as in 32 here. I'm doing the matrix multiplication with float, so I should do this properly. I should not look at them as float. This was correct. The values themselves are integers, but they are sort of the math happens on float because the vector is float. That's okay. Okay. So we have the blocked versions of the three arrays now uh, on the host and the device. We have filled up the arrays the three arrays. Now I'm just going to copy them to the GPU. First, I need to allocate them. So I'm going to copy this here. Yeah, let's put the assert 2 so that we're not doing something wrong. Should have probably used like a smaller suffix like underscore b or something instead of using underscore blocked. But hey. So this should, we added a alloc, we didn't add a assert. So I'm going to change this. I don't like when my rows are too long. So I'm gonna do this. All right, so this makes sure that we have the arrays. Now let's copy them, the blocked versions. I should have actually created a type which just has a pair of arrays inside, and I could just make a function on them called like toDevice or toHost, and they would internally do it. But I got lazy and I want to do everything manually. Okay, and finally, the bin offsets, we're going to keep them on the host. That's okay. And this should be fine. Let's see if this even compiles. Of course, it doesn't compile. 88. Mm, okay, it compiles. Now I'm going to just change the load graph call to also call the blocking thing. Wait, that's right. And then I'm going to provide a size of 20,000. We will iterate through this value and see which one is a good value. But for now, let's start with 20,000. And let's first see without anything if this works properly. If it messes with any of our existing ones. Okay, so the loading is going to take a while now because we need to do the whole blocking stuff. You could also dump the block matrix so you don't have to do it again and again. If it's taking too long, I can do that. There's also a other way to do this, which is instead of having iterate to the graph multiple times, you can iterate to the graph once and just put the non-zeros into the right location. You know what? Actually, I'll just change it to that. This is taking too long. Because it's going through the whole matrix like hundreds of times. We don't want to do that. So, okay. I'm going to fix this a little bit. Uh, dot h underscore bin offsets dot id. And this version requires us to have an extra, does it? No, this one doesn't require. So all of them are initializing to 0. And then I'm going to go through each non-zero exactly once. And then instead of doing like uh, which block it, I'm just going to determine which block it falls into. So this is easy to do. We can just say column ID divided by block size. So this just directly tells us which block size we are in, which block we are in. This is not required. And then, wait, what is this from? Okay, so now I can actually just say, I have the block ID. So now I need to know the location for that. So I'm going to say uint32t offset equals to g.h underscore bin offsets of block ID. Okay. And then I'm going to h underscore rows of offset set set required. And I'm going to do offset plus plus and store it back. Then I'm going to say g.h underscore bin offsets of block ID. Uh, so this directly puts it into the respective bins rather than having to like go over the graph multiple times. And hopefully this should load it faster. There we go. Now our loading is sufficiently faster and our other kernels are not being messed with. Now let's get to start writing our blocked kernel. So the block kernel, the way the implementation would work is we would do the exact same thing as EO does, but one block at a time. So void global spmv underscore EO underscore blocked. It's going to take the same parameters almost. So matrix T A float star T underscore B float star B underscore C. We don't need the numbers, but what we need is the offsets, the block start and the block end. So I'm going to say u int 32t block start, comma u int 32t block end. Okay. This is just going to give us like the non-zeros that we have to work with. And now I can do the actual iteration. So I'm going to copy these two exactly the same. And for int, now instead of starting from a thread ID, I'm going to do lnz id equals to thread id plus block start. So we start from this and we do uh, lnz id is less than block end. Lnz id plus equals to number. So this time we are like only doing through a part of that whole array, and this remains the same now, but we'll just use the blocked version of it, right? So d underscore rows underscore blocked, d underscore column underscore blocked, and d underscore values underscore. And this remains exactly the same. So for each kernel, for each one now, we're doing one block at a time. While calling the kernel, we launch them as different blocks. And for each block, then we are starting from the block start instead of from zero, and add thread ID to it, and then go up to block end, increase number of threads. For each of them, we'll access the blocked values, and we'll do it. This should work. And now we just have to write the call for this. So what I'm going to do is uh, copy this again. Running EO blocked version. All threads collaborative versus all in zero format. COO is partition into blocks for better locality. All right. This okay. Now the initialization remains exactly the same. The zeroing of the values remains the same. And now we actually need to iterate the block. So for int I equals, oh, we didn't store the number of blocks by the way in the matrix. So I need to store that too. U in 32t num blocks. Let me store this, right? Yeah, so this needs to go in the graph too. Okay, so we have int I equals to 0. I is less than g a dot num blocks I plus plus. Okay, so for each of the kernel now, we are going to run the blocked version. But we also need to tell it what the start and end is. So start and end is easy. For the first one, it's like, so, okay, so u in 32t blocks start equals to I equals 0, then it's 0. Otherwise, it is a dot h underscore bin offsets of I minus 1, right? Because the first one just starts from 0, we don't need this. And then u in 32t block n equals a dot h underscore bin offsets of I. So yeah, we know where each block starts and ends. Now we just pass it to this. So block start from a block end. And that's about it. I iterate through all the blocks. There's an implicit CUDA synchronize that will happen at the end. and everything should be fine now. Let's run this once and see if it runs properly. It produces the correct result before we do any sort of performance evaluation. I'm gonna call this block. Okay. Uh, this is actually one of the most interesting optimizations, by the way. This is very fun to implement and actually lets you see those improvements on those accesses. Okay, something is still wrong. Bunch of zeros, something not run properly. That's okay, we can fix that. Did our kernels even run? First, I'm going to run 0 here, so we can stop. And let's print something. Printf running block equals to right. And just make sure all the blocks are running. Yeah. Okay, so we have all the blocks running. That is great. Uh, Within each block, let's just print the start and end too. Right? Printf block bounds equals %d, comma %d slash n block start, comma block n. Okay, so the bounds are definitely wrong. This is not the right bound. So, okay, we made some mistake. We'll fix it. In offsets of I. We probably made a mistake here. So h underscore bin offsets of block ID equals to 0. Here block ID is column ID by block size. That is correct. Offset plus plus g underscore. Oh, no, this is fine. What are we doing here? H underscore bin offsets of I. Even these values. 829 to 51366, 513. Oh, we just stored the number of elements. We never did a sum of them. Okay, yeah, that yeah. So we stored how many elements each has. We never stored, like we never did a, like we didn't add the previous number of them. Yeah. So what we currently have is just how many non-zeros are per block. We never actually copied them over. That needs to happen next. So once we're done with all the non-zeros, we again go for int block ID equals to 0. We basically do a prefix sum on this, but we will do it the naive way this time. So uint 32t sum equals to 0. Block ID is less than num blocks. Block ID plus plus, and then we can say sum plus equals g underscore h underscore offsets of block ID, and then g dot h underscore bin offsets of block ID sum. Yeah, so this is gonna do the prefix sum of it. Let's see if this works properly. There we go. We at least have the last one reaching the million value that we needed. Let's see if this does the computation correctly now. So I can We can remove these and these. And let's remove this return so we can make sure that the computation that we did is correct. And okay, it's still producing zeros, which is bad. But our offsets are correct this time, so I just have to check this now. Why is it all zeros? Hmm. Okay, just to sanity check that code, what I'm going to do is I'm going to remove this, and I'm just going to say, let's just do all the non-zeros, right? If we made some mistakes in the kernel, this should not give the correct answer. Yeah, it's isolate where the problem is. Okay, it's still doing the wrong thing, which means, okay, the blocking arrays are not doing it correctly. Uh, let's just try to use the original values and see what happens. So using these, let's see if we just give it the original values. This should work properly, right? Now, this is essentially doing exactly what we were doing before. We did the blocking, but we discarded those values. Okay, this one runs correctly. Uh, let's do the blocking part. I think we made some mistake in actually doing the blocking. Uh, okay, this is running fine because we're still using the original array. So what's the problem with the blocking? Okay. Um, for each non-zero, the bin offsets have been initialized to 0, and then for column ID equals to g dot underscore h columns of NNZ block ID equals to column ID by block size, offset equals to bin, and then h underscore rows of offset is equal to g underscore row of NNZ G underscore column of offset equals to g underscore columns of NNZ Just place based on this should be fine. Unless I copied something wrong. H underscore rows blocks equals to H underscore rows underscore columns, H underscore values, right? The prefix sum looks correct. Going the wrong one. It's not going through all the non-zeros. That's what is happening. Or it's going through all the non-zeros but not doing the correct computation for some reason. Yeah, it's all zeros, right? Is there any non-zero in here? Oh, there are some non-zeros. Interesting. columns have been prepared, right? We take the column ID and we uh, divide it by the block size, which is 20,000. That gives us H value and column values. And then we store it at the right offset, which have all been initialized to 0. So we start from 0. Let's connect to me. What did I mess up? What did I mess up? Like if I do the whole block start block end thing, but I just don't use the blocked values, does it work properly? Maybe I made a mistake in the kernel somehow. Uh, RID equals to D underscore rows of block and NZID columns and then block value block. This seems fine. What happens if I don't use the blocked version? It's the same as before, right? Okay, this one does run correctly. So then did I allocate enough value for them? None values, none values, none values. This is correct. UN32, UN32, UN32. This is also correct. Hmm. H underscore bin offsets. Okay. I'm gonna quickly look at the implementation. This is something I have written before, so I don't know why I'm making a mistake with it, but uh, doesn't hurt to check. It's in graph.h. So initialize all of them to 0, then block ID. Okay, you just go through all the edges to it, do the running sums. Oh, of course, because we need to do the running sums first. Okay, yeah, this was my mistake, folks. So we first need to do the running sums to identify how many each of them has, and then we need to write them. Yeah, that's the mistake. Sorry. So we initialize them to 0, but that's not good enough. We need to go through all the non-zeros first. Before we actually copy the values. We're currently copying them over and over at the same location because all the blocks don't know where they start. So this gets copied here and uh, this gets copied here. So I guess the only way to do this is easier to do it, just to do this here. So we count for each one of them how many they have, and then we do the prefix sums, right? So now for each row, we know where they start. But yeah, for this one, we actually need to do the num plus one trick now so that we have the old values too. So I'm gonna do We're going to start from 0 for all the blocks, increment all of them by 1. So at the end of this, we will know how many each of them has. Uh, no, actually, we need to increment the one for the next one, right? Yeah, block ID plus 1. So we're going to increment this for the next one, not for this one. And then we do the prefix sum that goes up to block size plus. So the 0 also always remains 0. The size of the previous one becomes the start of the next one. So yeah, this is fine. And now we already have our values, so we can just use them as offsets. And by the end of this, all of them will have their values pushed to the edge. Okay, let's see if this works. Sum is undefined. 107. Define the sum below. Yeah, I wrote this code like years ago, 3 years ago. So it's not surprising that I made a mistake. I'm sure I made the same mistake when I wrote that the first time too. But bear with me. There we go. Did we actually do this correctly this time? So blocked is copied in the SPMV kernel. We are using the blocked version and we are doing the blocks correctly. Great. Now let's actually increase the times we run this and see how well or worse it performs. I guess it's going to perform worse, but we fix it. Running sums, this stream went from parallel algorithms to streaming window domain. No, it's not really. It's the running sum as in like it's for the prefix sum. That's the running sum, not, yeah, I mean, we are streaming through the whole graph once in some way. So yes, it is like that, but the goal is different. Okay, so we did a blocked version and it ran slower than before. So why did that happen? It's because we haven't tuned our block size correctly yet. So let's do that now. Actually, my kernel launch parameters are correct, right? Okay, yeah. Let's tune our blocking size and see if that improves performance. So we're currently separating it out into 20,000 vertices, 20,000 elements. 20,000 multiplied by this is a UN32 that we are loading from the vector float wave loading. So 20,000 into 4 is 80,000 bytes. If we divided that by 1024, that's just 78 kilobytes. How much in the V100 last level cache? I think we have more. We have a lot more actually, so we should be doing more at a time. Okay, here we go. V100. L2 cache size. We have 6144 kilobytes, which is a lot more than what we're using. We're currently using only 78 kilobytes. So we have almost like 10 times of this. So what I'm going to do is I'm going to make it 20,000 and see if that helps in any way. Sorry, not 20,000, 200,000. There we go. Performance has slightly improved over the previous version. We can further tune it. We can try some values in the middle, and one of these would give us better performance. I can pull up the exact values that we ran it with, but this is slower. So maybe 20,000 was actually fine, but maybe the number of blocks we can tweak. So let's see if adding more parallelization helps. There we go. So it's much better than our 493 number before. It's at 438 milliseconds. I think we can do better than this. I have to further tune the numbers. Uh, let's try actually more block size. The block Try 300,000. Wait, did we do the math correctly? 78 and 6. Oh, we can actually go much more. We can go to 800,000. This should also fit in the cache. I'm just trying to see how much of data we can fit in the last level cache before we have to start directing again. Usually we use like some sort of auto. Yeah, so it's getting better. I think we can further go up to 100,000, a million. And we can store a million vertices in our cache before we have to evict them. Yeah, it's 6 MB, right? Yeah, 6144 is 6 MB. I think it's reaching its edge now. How much is this? I think this is 4 MB. You also have to leave some memory for the ground database. Yes, this is 39006. We can actually try a little bit more ambitious. This should probably work. But there's a right balance. You have to tune these parameters. It's not going to automatically give you. Okay, this is bad. Let's keep it at 100, and maybe these blocks were too many. Yeah, the rule one of programming GPUs is you can never predict the parameters correctly. You always have to guess them. You have to try a different one till you get the best performance. I don't know of any other method by which you can get right values. This is still bad. Did we get, we got good with 80, right? Like 80,000. 800,000, sorry, 800,000 vertices loaded at a time. Wait, what was it that gave us? Come on, we had 386 with something. Is it with 160 blocks? Yeah, maybe I'm only utilizing half my GPU. So my GPU has 80 SMs, and each SM can hold 1024 threads at a time, maybe even more. So we should be occupying it completely if we can. There we go. 380, 390 is, I think, the closest we can get. I'm just going to look at the paper and see what numbers we had for this specific kernel. And if it's close to that, I'm going to call it a day. So let's see. Let's go to my papers. Uh, Here we go. This was our paper, by the way. Uh, we made a compiler for compiling these applications. Okay, so for the V100 GPU, our page rank, which is SPMV, ran for live journal in 3.76 milliseconds per iterations. And we have reached 3.90. This is 100 iterations, so 3.90. What I'm getting at is like some more tweaking will get us a little bit faster. I can try, or I can like, you know what, actually, I can just pull up my artifact evaluation directory, and that has everything. That has all the parameters that we use to run these applications. So graphic eval, v2 eval, gen table 7. Yeah, so all our parameters and everything is in this thing. So run PR. Hmm, or something else. Okay, no, small PR. Uh, Compile and run PR. It's the PR code executable. Where's the run file? Oh, I guess it doesn't have parameters then, which is baked into the input files. Table 7 inputs, page rank.gt. So yeah, it's baked here. So yeah, this is the magic number that gives us the correct best performance. So how did I come up with this? By trial and error mostly. And we'll still have to tune the number of threads we launch, but that's for later. Hmm. Maybe I can launch more threads. Nah, this is not. Hey, this is for the V100 GPU, right? Yeah. Uh, this is doing the same thing. I think I'll have to play with these numbers a little bit more, and one of them should give me the right values. Uh, okay, but we are close. I think there's this like some implementation difference that's uh, I'm gonna stick with like the 80,000, 800,000 value and whatever performance that gives us. Yeah, you don't have to dip. The value doesn't dip. The value of that block size doesn't actually depend on. It doesn't depend on the graph itself. It only depends on the GPU parameter. So that's why it was like baked into the algorithm itself. Like I mean, what I was going through before was um, Graphite is a language, right? It's a compiler and a language to write these applications. So we basically have inputs like these, like say the PageRank algorithm that's implemented as this language of our own. So we have like the core computation that's happening here is still the same. You're doing basically plus equals to on the ranks. And it's SPMV essentially. And we have a separate scheduling language that lets us specify how to compile this down. So we have a simple GPU schedule S1. We are setting the direction to be pull. What pull means is in this case, each edge is going to fetch the value from the destination and add it back or send it back to the source. So that's the pull iteration. And then the load balance is edge only, which is what we did here. And then it's blocked because we have block, and this is the blocking size parameter. And then we apply this schedule to this statement where the function is being invoked. And that's how we generate very different codes. So if you look at the codes that's generated for this, I hope I have this compiled. I don't. Oh well. Uh, Let's see. Let's quickly compile this. I don't even, I just had this built then. I didn't even have it built, sorry. I think just default CMake should be fine for now. Oh, the problem is this won't run because I don't have a GPU locally that can run this. You know what? I'll just go to the. I have it compiled, right? I should have it compiled. I mean, some GPU backend. I have the merge one. Last time. No, there we go. This is on the right one. It's called master, but so if you go to this directory, table 7, let's look at the outputs, right? So table 7 outputs. Yeah, so when you compile our code, it produces simple. Yes, this is not compiled either. Let's do Python 3 gen table 7. Oh, user local CUDA 11.4. I'm trying to make it generate the code so we can look at it. But yeah, that's where I'm going to like wrap up the optimizations. Come on, what did I miss? Not load the data set. It doesn't have the matrix. I deleted the local data set from my side. But you know what we can do? We can just change the script to just compile the code. I don't want to run actually anything. So let's do this. Mm, run underscore PR. Actually, it must have generated the code now, right? Because it tried to run it. What did it fail on? Oh, it failed on the load thing. Let's not run sanity checks because that's what it fails on. Uh, Copied the wrong path. Sorry, this has been a while. Now it should run correctly. Okay, running evaluation for page rank. So now it should crash and it should generate the code first. So that's what we're looking for. Uh, Okay, now if you look at table 7 outputs, yeah, it has the implementation for the page rank generated. This is all compiler generated code. It does similar stuff to what we wrote, but you can see that it launches this edge only load balance host kernel, which basically internally has like the blocked edges and everything. It has like template parameters to tell it what exactly needs to be done. And what needs to be done is this GPU operator body 4, which has this update edge call, and the update edge is doing this, yeah, GPU runtime colon write add. So this is very similar to what we wrote. It's just generated through a compiler. This is all generated code. This is not handwritten code. And yeah, there's some parameters here and there different that's causing the performance to be slightly off. It's not too much off. It's like, how much is this? 3.9 milliseconds, and that is 3.76 milliseconds. So uh, yeah, small compiler changes version, okay, 3.89. So the compiler version changes also could do that. So yeah. Anyway, point being, this is, I think, the best we can do for this graph anyway. I mean, when I was doing this research, I spent a lot of time trying to optimize this. But yeah, so that's where I think we close our optimizations for SPMV. If you folks are interested, I can also touch more sparse kernels. Like we can go into SPM, SPV, although we are closing the end of like 4 hours for today's stream. So I think I'm gonna wrap it up here for today. I'll send all the resources, the paper links, and I'll also put I'll push the code that we wrote today. And yeah, there were a bunch of resources shared in the chat, so I'll share those too. Um, and yeah, and like someone requested, I'm going to like maybe write down the explanation of how the prefix sum works, and I'm going to put an image either of the hand-drawn one, or I'll put like something that's made in like a better tool and put it in the resource directory, and hopefully that's easier to read. Yeah, the prefix sum is a pretty interesting kernel. I think when you think about GPUs, there are like for normal applications, right? Like there is a straightforward way to do things, and that's usually the best way. Like if you have to sum up values in an array, the easiest way is to just iterate through them and sum them up. But when you have this massive parallelism available, if you're not using that parallelism, you're losing on performance. And in the same way, like doing prefix sum, if you do it using a single core, these cores are super, super, super weak. I mean, they're not running at like 3 gigahertz or whatever your normal CPU is running at. So if you just try to do it on on one of the cores of the GPU, your performance is really going to be trash. So yeah, that's you do prefix sum with GPUs. Prefix sum using SIMD, that's my limit. Yeah, I mean, what we exactly did actually is very much like SIMD. It's not it's GPU. It's still written using a thread model, but you can write the same code using vector operations too. Because what we are doing is essentially like exchanging values up and down. You can do that as shuffle masks. Like Intel has new instructions where you can like do arbitrary shuffles between lanes of your vectors, and you can do that. You can like create those exact masks that will send the values like one up, two up, and so on. Sorry. I hope that wasn't too loud. You can create those masks exactly that can let you do like this very fast prefix sum on CPUs with vector instructions. We also have an implementation of the prefix sum which doesn't do it on one CPU on just within the warp, but across the whole CTA. So if you look at this implementation of our, so what we implemented today was the load balance WM, right? Yeah, the load balance WM is what we implemented. So this has like a prefix sum that sums up those values within the warp. But we also have CM, which is uh, it's called CTM mapping, or hold on, why is this showing up? Um, it's called CTM mapping, which is basically trying to balance the load for all the threads within a block. And that actually has a prefix sum that goes across the whole block. It starts off by doing the prefix sum within the warp, the same thing, and then it sort of does the whole same operation across the whole sort of block. And yeah, I mean it has similar steps, but like at a more coarser granularity. It's more complicated than the CM one, so I didn't want to touch this one today. I would make more mistakes if I was trying to do this. But essentially, this does the whole prefix sum across the whole block, and then the rest of the computation is exactly the same. You do a binary search in the block, and then you do your computation. So it's but the difference here is that instead of doing 32 at a time, you're doing the whole block dimension at a time, which is it addresses different types of load balance. So like what matters is it depends on the graph, and it depends on the graph or the matrix and the distribution of non-zeros you have in each row. If your distribution of non-zero is like each row has about like say 100 or 500 non-zeros, then this kind of a balance works better. If you have fewer, then the WM works better. If it is even less, like if each each non-zero has like one or two non-zeros, then it's better to just map them to each different to do different threads basically. As far as my understanding, GPU algorithms are data oriented. SIMD is just a small data oriented ALU on a CPU. Uh, Yes, I mean, maybe I'm not understanding what you're saying correctly, but GPU SIMD is SIMD is a terminology for describing types of architectures, right? Like or types of operations even. SIMD is single instruction multiple data. In a way, GPUs are SIMD. They are single instruction multiple data because they are executing in lockstep. But the terminology that they like to use is SIMT, which is single instruction multiple threads. This is not like writing vector instructions, right? You're not loading multiple values and dealing them with the same variable and so on. What you're doing is you have this abstraction of having different threads. You have different threads with their own registers. You have the different threads with their own program counters, and they can do different things. Like each thread has a branch. The branch can do different things for each thread. Underneath it sort of can execute it as one instruction at a time. That's why it's single instruction multiple threads. But a lot of performance techniques that you apply are actually shared with SIMD, because in SIMD 2 you don't want like your computation to diverge too much. If it diverges too much, then you're sort of like executing different instructions, and you have to like suppose you're doing element wise sum of two vectors using SIMD. That's great because you're adding respective elements. But now suddenly suppose you have to do element wise sum for half of them and element wise multiplication for half of them. So now what you would have to do is like, okay, I'm gonna do the sum on all of them, but I'm going to mask some of the lanes, and then I'm going to do a product on the other ones. I'm going to mask the first lanes, which means I have to do two different computations now, and that kills your performance. So in the same way, the performance considerations are exactly the same for GPUs and CPUs with SIMD registers. It's just the programming model is very different. Like for example, now you just call this function shuffle sync. There you would have to write shuffle like masks to actually exchange those values. And this actually is faster. Like this doesn't have that bad performance as having to create a mask and then apply it. But anyway, that's more into like differences and similarities between SIMD and GPUs. Um, The other major difference is GPU bandwidth, memory bandwidth is super high, which is not the case for CPUs with SIMD registers. You still have the same amount of bandwidth that you have for a normal CPU, and that actually is it's not suitable to do the exact same algorithms. You can there's a set of algorithms that are common, but not all algorithms can be written with SIMD CPUs and get the same performance out of them. Anyway, I think this is where we'll wrap up for today. I think it's 4 hours. I have been speaking for 4 hours, and my throat is really dry. But I'll announce soon when the next stream would be. I have to figure out some topic. I think this GPU sparse computation sort of like reached a stage where I have covered a lot of things that I wanted to. Like I want to talk about load balance, I want to talk about blocking, I wanted to talk about different formats and how much performance you can gain out of them. I think there is more to be done, obviously. Like we have an entire paper with like 10 different optimizations and 15 different applications and everything. But I don't want to get into too much of that detail. But if you're interested, I can continue a GPU series continued ahead. Or I can pick up something else. I have like I could go into Build It and I could talk about how you can use Build It's capabilities to even optimize for GPUs. We actually had not a paper, but it was like a research project where we used Build It to generate efficient GPU code for better utilizing your instruction cache and data cache. Like we had a very fancy technique for that. I could talk about that and how Build It made that writing that code implementation very easy. If you're interested, I'll actually do a poll on Twitter maybe to figure out what we want to do next. GPU bandwidth is also limited by PCIe bus. Yes, it is. GPU bandwidth essentially, I mean, GPU is plugged into your PCIe, so bandwidth is limited by that. But the PCIe bandwidth is typically higher than your CPU to main memory bandwidth. That is much larger, the bandwidth on PCIe. So it's directly connected to the host memory, right? It's not connected to the CPU. So the GPU is not directly transferring data from GPU to the host memory. But here's the thing: when I say GPU bandwidth, I don't mean the bandwidth between the host and the GPU. I mean the bandwidth between the GPU DRAM and the GPU chip. That's different. Like that's actually much higher than even the PCIe. It's much higher than the PCIe bandwidth. It's the bandwidth. So the GPU has its own DRAM. Like in fact, a better DRAM than your normal CPU's like main memory. It's on the GPU itself. And that's why when we say I bought a GPU with like 16 gigabytes of memory, that's the host, that's the GPU's DRAM. And the bandwidth between the GPU DRAM and the GPU chip where the compute happens is what matters. And that's much higher than PCIe or CPU's bandwidth and so on. Yeah, so maybe I was using confusing terminology, but yeah. Anyway, so yeah, let's wrap it up for now. And I'll send out links, I'll upload it to YouTube, and I'll see you guys next week probably. Thanks.